In the vastness of the universe, where countless stars shine in the night sky, there exists a phenomenon so rare and fascinating that it challenges everything we thought we knew about the cosmos. Picture this: not one, not two, but four stars locked in an intricate celestial dance, defying the odds of physics and probability. These are quadruple star systems, cosmic wonders that push the boundaries of our understanding. Today, we embark on a journey through 50 strange and awe-inspiring discoveries about these systems, each one unraveling a new layer of mystery. From planets with multiple sunrises to stars that seem to play a game of gravitational tug-of-war, we will uncover secrets that will leave you questioning the very nature of the universe. Stay with us as we reveal the extraordinary and the unexpected, shedding light on the enigmatic beauty of quadruple star systems. By the end of this video, you will see the cosmos in a way you never imagined possible. Keep watching to join us on this cosmic adventure. As we turn our gaze to the first major discovery in our cosmic journey, let us take a moment to appreciate how astronomy often reveals its treasures in the most unexpected ways. The first known quadruple star system was identified through a combination of curiosity and meticulous observation, a testament to humanity's relentless pursuit of the unknown. This groundbreaking find occurred when astronomers noticed unusual patterns of light from a distant star. At first glance, it appeared to be a binary system, but further investigation uncovered something far more complex. Not one, not two, but four stars were found intricately intertwined in a celestial ballet. This revelation challenged long-held assumptions about how star systems form and interact. The discovery not only expanded our understanding of stellar mechanics, but also opened new avenues of research into the dynamic interactions within multi-star environments. It was a moment that reminded us just how much there is still to learn about the universe. With this newfound understanding, astronomers began rethinking theories about stability, orbits, and even the potential for planets in such systems. Now, let's step forward into a deeper exploration of how these stars manage to maintain their delicate balance, setting the stage for our next intriguing insight. Stepping into the heart of what makes quadruple star systems so fascinating, we encounter a concept that feels almost architectural in its precision: the hierarchical structure. At first glance, imagining four stars orbiting one another might evoke visions of chaos, but nature has a way of finding balance even in the most intricate scenarios. What keeps these systems from tearing themselves apart is a remarkably organized arrangement. Picture this like a cosmic dance where pairs of stars are grouped into smaller binary systems, and these binaries then orbit a common center of mass. It's a bit like partners in a dance team moving together while also staying in sync with the larger group. The stability of these systems relies on this layered approach, where each star maintains its own orbit within its immediate pair, and the pairs themselves follow a wider orbital path around each other. This hierarchical design minimizes destructive gravitational tugs and allows the system to remain stable over astronomical timescales. To break it down further, think of it as two separate binary systems, each with two stars locked in their own gravitational embrace, that then behave like a single entity on a much larger scale. The result is a delicate yet durable balance that defies the odds. It's this ingenious structure that allows quadruple star systems to exist at all, and it raises intriguing questions about the limits of stability in multi-star environments. As we piece together how these systems hold themselves together, we begin to see just how much the universe values order, even in its most crowded corners. And this understanding sets the stage for our next discovery, where we'll explore the tantalizing possibility of planets forming and surviving in such complex gravitational arenas. Now that we've unraveled the delicate balance that allows quadruple star systems to thrive, it's time to turn our gaze to an even more tantalizing question: could planets exist in such intricate cosmic neighborhoods? The idea of worlds orbiting not one, not two, but four stars might sound like science fiction, yet it's a possibility that astronomers are actively exploring. And as we dig deeper, the implications for life, habitability, and the very nature of planetary formation become more profound than ever. While the gravitational ballet of four stars seems like a recipe for chaos, simulations suggest that certain regions within these systems could provide stable environments for planets to form and endure. These regions, often referred to as safe zones, are areas where the combined gravitational pull of the stars evens out enough to allow a planet to maintain a consistent orbit. But here's the twist. These safe zones can exist in surprising places, such as around one of the binary pairs or even far beyond the orbits of all four stars, in a distant circumbinary configuration. One of the most fascinating examples comes from computer simulations that model how planets might behave in these systems. Imagine a world orbiting a single star within one of the binary pairs. If that star isn't too close to the other stars, the planet could experience a relatively stable orbit, despite the gravitational influence of the neighboring binary pair. In fact, these simulations show that the planet might even have a chance at maintaining conditions suitable for water, and perhaps life over billions of years. But the complexity doesn't end there. Picture a planet orbiting not one of the individual stars, but all four of them, tracing a wide, looping path far from the chaotic center. This is called a circumbinary orbit, and while it might seem precarious, such setups can be surprisingly stable under the right conditions. It's like a cosmic tightrope walk, where the forces pulling on the planet balance each other out just enough to keep it in place. But let's not get lost in the theoretical. There's real evidence that such systems might exist. Astronomers have already discovered planets orbiting binary star systems, so-called Tatooine planets, named after the fictional world from Star Wars. Extending this concept to quadruple systems isn't as far-fetched as it might seem. In fact, some researchers suggest that planets could form in the outer regions of these systems, where the gravitational chaos is less intense. These planets might be icy and cold, far from the warmth of their host stars, but they would still offer a glimpse into the adaptability of planetary systems in extreme environments. The implications for habitability are equally mind-bending. Imagine a planet with not one or two sunrises, but four, as each star takes its turn lighting up the sky. The climate on such a world would be a complex dance of light and shadow, with seasons dictated not just by the planet's tilt or orbit, but by the intricate motions of its multiple suns. While the likelihood of liquid water and by extension, life might be slim in these exotic locales, the idea challenges our assumptions about where life could take root. And as we refine our understanding of these systems, we're reminded of just how much there is to learn about the universe's capacity for creativity. With this glimpse into the planetary possibilities of quadruple star systems, we're left to wonder, what other surprises might these cosmic neighborhoods hold? To answer that, we'll need to look even closer at the stars themselves, starting with a phenomenon known as eclipsing binaries, which offer a unique window into the inner workings of these stellar quartets. Shifting our focus to a particularly fascinating feature of quadruple star systems, we arrive at a phenomenon that allows astronomers to unlock some of the universe's best-kept secrets, eclipsing binaries. These are pairs of stars that, from our vantage point, periodically pass in front of one another, causing their light to dim in predictable patterns. When these eclipsing binaries are part of a quadruple system, they become even more extraordinary, offering a rare chance to measure the physical properties of stars with remarkable precision. The magic of eclipsing binaries lies in their geometry. As one star passes in front of its companion, it blocks a portion of the light that reaches us, creating a dip in the system's brightness. By carefully analyzing these dips, scientists can determine key details such as the star's sizes, masses, and even their distances from one another. In quadruple systems where two binary pairs are gravitationally intertwined, these measurements become a gateway to understanding the intricate dynamics at play. Imagine trying to weigh and size stars that are trillions of miles away. Eclipsing binaries make this seemingly impossible task not just feasible but remarkably accurate. What makes this even more exciting is how these systems challenge our understanding of stellar evolution. By observing eclipsing binaries within quadruple systems, researchers can compare the properties of stars in close proximity to those farther apart. This comparison provides clues about how gravitational interactions between the stars influence their growth and aging processes. For instance, stars in tight binary pairs might age faster due to the strong gravitational pull from their companions, while stars in wider orbits could evolve at a more leisurely pace. These differences help paint a more complete picture of how stars live, change, and eventually die when they're part of such complex families. One of the standout examples of this phenomenon is a system that has captured the attention of astronomers worldwide. By studying its eclipsing binaries, researchers were able to calculate the masses and sizes of its stars with an accuracy that rivals laboratory measurements. This level of detail is invaluable because it allows scientists to test and refine their models of stellar structure and evolution. In a way, these systems act like natural laboratories, giving us front-row seats to the forces shaping the universe. But the significance of eclipsing binaries doesn't stop there. They also provide a unique opportunity to probe the stability of quadruple systems. The precise measurements enabled by these eclipses can reveal subtle changes in the orbits of the stars, hinting at the gravitational tugs and pulls occurring within the system. This information is crucial for understanding how these systems maintain their delicate balance, or, in some cases, spiral into chaos. As we peel back the layers of these celestial puzzles, we're reminded just how interconnected and dynamic the universe truly is. With eclipsing binaries offering such a wealth of insight, it's no wonder they've become a cornerstone of modern astronomy. Yet, as powerful as these tools are, they're just one piece of the larger cosmic jigsaw. To truly grasp the full complexity of quadruple star systems, we need to explore another groundbreaking discovery, one that brings us closer to answering the age-old question of whether planets in such systems could harbor life. This brings us to the remarkable case of KIC 48622625, a quadruple system that holds one of the most intriguing secrets of all, a circumbinary planet. As we venture further into the cosmic wonders of quadruple star systems, we encounter a discovery that stretches the boundaries of our understanding of planetary formation and survival. This is the story of KIC 48622625, a system that defies expectations and redefines what we thought possible for planets in multi-star environments. Within this complex system lies a circumbinary planet, a world that orbits not one but two stars at the same time. It's a concept that sounds more like science fiction than science fact, yet here it is, confirmed by meticulous observations and groundbreaking research. KIC 48622625 is a quadruple star system composed of two tightly bound binary pairs, each dancing around the other in an intricate gravitational ballet. What makes this system extraordinary is the presence of a planet, often referred to as PH1, which resides in a stable orbit around the primary binary pair. This planet exists in a delicate balance, influenced by the gravitational pull of not just its host stars but also the distant companion binary. For astronomers, this is a treasure trove of information, offering a rare glimpse into the dynamics of planet formation in such chaotic environments. The discovery of PH1 challenges long-held assumptions about where planets can form and how they can endure in systems with multiple stars. In a typical binary system, the gravitational forces can create unstable regions, making it difficult for planets to maintain stable orbits. Yet, here we have a planet that not only formed but also persists in a region where its very existence seems improbable. This raises fascinating questions about the conditions that allowed it to emerge and the factors that keep it in place. Could there be other circumbinary planets hiding in similar systems, waiting to be uncovered? The implications of this discovery extend far beyond the system itself. KIC 48622625 provides a unique opportunity to study how planets interact with their host stars and neighboring stellar companions. By observing the orbital dynamics of PH1, scientists can test theories about planetary migration, the distribution of material in protoplanetary disks, and the long-term stability of circumbinary orbits. These insights are invaluable for refining models of exoplanetary systems, particularly those in multi-star configurations, which are more common in the universe than we once thought. What's truly remarkable about this discovery is how it bridges the gap between theoretical predictions and real-world observations. Before PH1 was detected, circumbinary planets were largely theoretical, their existence inferred from simulations but never directly observed. Now, thanks to the Kepler Space Telescope and subsequent studies, we have concrete evidence that such planets are not only possible but may be more widespread than we imagined. This opens up exciting possibilities for future research, as astronomers continue to search for more planets in quadruple star systems and beyond. As we marvel at the complexity of KIC 48622625 and its circumbinary planet, we're reminded of the universe's infinite capacity to surprise us. It's a humbling realization that even in the most chaotic and crowded corners of space, the conditions for planetary formation can still arise. And with each new discovery, we edge closer to answering one of humanity's most profound questions: could such worlds harbor the ingredients for life? With that thought lingering in our minds, we now turn our attention to another captivating aspect of quadruple star systems: their chaotic orbital dynamics, where stability is anything but guaranteed. As we shift our gaze from the delicate balance of circumbinary planets, we find ourselves staring into the cosmic maelstrom of chaos that defines some quadruple star systems. These systems, far from the orderly dance we might expect, are a testament to the wild and untamed forces of gravity that govern the universe. In certain quadruple systems, the gravitational tug-of-war between stars creates a dynamic environment where predictability is a rare commodity. The intricate interplay of forces can send stars on wildly erratic paths, making their future positions nearly impossible to forecast with precision. Imagine a game of celestial pinball where the stars are the balls, ricocheting off each other in a complex and ever-changing pattern. In these chaotic systems, even the smallest deviation in the starting positions or velocities of the stars can lead to vastly different outcomes over time. This sensitivity to initial conditions, often referred to as the butterfly effect, is a hallmark of chaotic systems. Gravitational interactions in quadruple star systems amplify this effect, introducing a level of unpredictability that challenges our understanding of orbital mechanics. What makes this behavior particularly fascinating is how these gravitational tugs can lead to dramatic events, such as the ejection of a star from the system. Picture a scenario where two stars in a tight binary pair grow too close to another pair. The resulting gravitational slingshot can hurl one of the stars out into the depths of space, leaving the remaining stars to reconfigure into a new, often more stable arrangement. These ejections are not just cosmic accidents, they are a natural consequence of the delicate balance between order and chaos in these systems. Yet, for all the unpredictability, there are moments of fleeting stability. In some cases, the chaotic interactions can temporarily settle into a quasi-stable state where the stars find a rhythm, albeit a precarious one. These periods of calm can last for thousands or even millions of years, giving astronomers a brief window to study the system in relative equilibrium. However, these moments are often short-lived, as the relentless forces of gravity eventually push the system back into chaos. The study of chaotic orbital dynamics in quadruple systems isn't just about unraveling the mysteries of distant stars. It has profound implications for our understanding of the universe. These systems serve as natural laboratories where scientists can test and refine models of gravitational interactions and orbital mechanics. By observing how these systems evolve, we gain insights that can be applied to a wide range of celestial phenomena, from the formation of galaxies to the behavior of black holes. And so, as we reflect on the chaotic dance of stars in quadruple systems, we are reminded of the delicate balance that governs the cosmos. It's a balance that, while often chaotic, holds the key to understanding some of the universe's most profound secrets. With that in mind, let's continue our journey into the rare and challenging task of identifying these complex systems spectroscopically, where the true test of observation meets the art of astronomical discovery. Now that we've explored the chaotic dance of stars, let's turn our attention to the intricate challenge of spotting these quadruple systems in the first place. Identifying quadruple star systems spectroscopically is no small feat. Unlike binary systems, where the back and forth motion of two stars creates a relatively straightforward pattern in the light spectrum, quadruple systems are far more complex. With four stars in motion, their overlapping signals create a tangled web of spectral lines that can easily confound even the most advanced instruments. For decades, astronomers faced immense difficulty in separating the individual contributions of each star. The light from these systems often blends together, creating what appears to be a single, chaotic signature. Early spectroscopic methods struggled to resolve the subtle shifts in wavelengths that reveal the presence of multiple stars. This made quadruple systems not only rare to detect, but also prone to misidentification as simpler binary or even single-star systems. Imagine trying to hear four people speaking at once in a crowded room. That's the kind of challenge astronomers face when analyzing the light from these systems. However, the story doesn't end there. Thanks to technological advancements, the tide has turned. Modern spectrographs, equipped with higher resolution and precision, have revolutionized the search for these elusive systems. Instruments like the High-Accuracy Radial Velocity Planet Searcher, or HARPS, allow astronomers to pick apart the faint wobbles in a star's motion caused by the gravitational pull of its companions. These tools can detect minute shifts in spectral lines, revealing the presence of additional stars that were once hidden in the noise. Even more exciting is the role of space telescopes, such as the Gaia mission, which has been meticulously mapping the positions and motions of stars across the galaxy. Gaia's ability to measure tiny changes in a star's position has uncovered new quadruple systems by revealing the gravitational influence of unseen companions. These advancements have not only increased detection rates but also provided a deeper understanding of how common and how unique these systems truly are. Despite these breakthroughs, spectroscopic identification remains a rare and demanding process. It requires not just cutting-edge technology, but also a healthy dose of patience and ingenuity. Yet, the rewards are immense. Each new discovery adds another piece to the cosmic puzzle, helping us understand the intricate interplay of forces that govern these systems. And with every quadruple system identified, we move closer to answering fundamental questions about star formation, gravitational dynamics, and the structure of the universe itself. As we celebrate these technological triumphs, we now turn our gaze to the magnetic fields that shape the environments of close quadruple systems, where the interplay of forces takes on yet another fascinating dimension. Shifting our focus now, let's unravel another layer of these cosmic marvels by diving into the role magnetic fields play in close quadruple star systems. Magnetic fields might seem like an invisible force, but in these systems they shape the environment in remarkable ways. Picture this: stars are not just glowing orbs of gas but also powerful dynamos, generating immense magnetic fields that stretch far into space. In close quadruple systems where stars orbit near one another, these magnetic fields interact in fascinating and sometimes dramatic ways. Consider how these fields influence stellar winds, the streams of charged particles that stars constantly release into space. Each star in a quadruple system contributes its own wind, and when these winds collide, the results can be spectacular. The magnetic fields guide and shape these winds, sometimes creating shock waves where the streams meet. These interactions can heat the surrounding gas to extreme temperatures, causing the system to emit high-energy radiation like X-rays. It's almost as if the stars are locked in a constant cosmic battle, with magnetic fields acting as both shields and weapons. But the effects don't stop there. Magnetic fields also alter the radiation environment around these systems. For instance, if a planet were to exist within or near such a system, the intense radiation shaped by these fields could strip away its atmosphere over time, making it a harsh and inhospitable place. This raises intriguing questions about the habitability of planets in quadruple star systems and how these magnetic forces might influence the delicate balance required for life. What's particularly captivating is how astronomers study these magnetic interactions. By analyzing the light emitted by these systems, especially in wavelengths like radio and X-rays, scientists can piece together the invisible puzzle of magnetic activity. These observations reveal not just the presence of magnetic fields, but also their strength and structure, offering insights into the dynamic processes at play. As we contemplate the interplay of magnetic forces in close quadruple systems, let's now turn our attention to the even bigger question of how these complex systems come into existence in the first place. This brings us to the intriguing topic of formation theories, where we'll explore the competing ideas about what gives rise to these stellar quartets. Now let's journey into the origins of these stellar ensembles and explore the intriguing question of how quadruple star systems come to be. The creation of these systems is a cosmic puzzle, and astronomers have developed several theories to piece it together. At the heart of the debate are two leading ideas: fragmentation models and capture scenarios. Both offer compelling explanations, but they paint very different pictures of how these celestial quartets are born. Fragmentation models suggest that quadruple star systems form from the same massive cloud of gas and dust, much like how single stars or binary systems take shape. Imagine a vast, swirling nebula collapsing under its own gravity. As it contracts, the material inside begins to clump and fragment into smaller, denser regions. These regions eventually evolve into individual stars. In the case of quadruple systems, this fragmentation process results in 4 distinct stellar cores forming within the same region. The stars then settle into a hierarchical orbital pattern, maintaining a delicate balance as they revolve around one another. This theory aligns well with observations of young stellar groups, where multiple stars often emerge together from shared birthplaces. On the other hand, capture scenarios propose a more dramatic and chaotic origin. According to this idea, quadruple star systems are not born together, but instead come into existence through chance encounters. Picture 2 binary star systems wandering through space, each minding its own business, until a close gravitational interaction brings them together. If the conditions are just right, think of it as a cosmic dance. They can become gravitationally bound, merging into a single quadruple system. This scenario is less common than fragmentation, but adds an element of unpredictability to the universe's creative processes. It also highlights how dynamic and ever-changing space can be, with stars occasionally finding new partners in their celestial journeys. Both theories present fascinating possibilities, and in some cases they might even work together. For instance, a quadruple system could start with fragmentation, forming 2 pairs of stars, and later undergo a capture-like interaction if the pairs drift close enough to one another. This blend of processes underscores the complexity of stellar formation and shows us that the universe rarely sticks to a single script. understanding which of these theories holds more weight requires studying the properties of known quadruple systems. By analyzing their orbital patterns, ages, and compositions, scientists can test these models and refine our knowledge of how such intricate systems develop. It's a reminder that even in the vastness of space, every star has a story to tell about its beginnings. And as we uncover these stories, we edge closer to solving the mysteries of the stellar nursery. Speaking of mysteries, our next discovery will take us deeper into the complexities of these systems, focusing on a specific quadruple system that has intrigued astronomers with its unique protoplanetary disk. This will shed light on how disks of gas and dust influence the formation and evolution of these stellar quartets. Now, let's shift our gaze to a truly captivating example that brings these ideas to life. At the heart of this discovery lies HD 98800, a quadruple star system that has fascinated astronomers with its remarkable protoplanetary disk. This system offers a unique opportunity to study how disks of gas and dust behave in environments with multiple stars, providing clues about the intricate dance between stellar companions and their surrounding material. HD 98800 consists of two pairs of stars, each locked in a tight orbit with its partner. Around one of these pairs lies a sprawling disk of dust and gas, a remnant of the system's formation. What makes this disk so unusual is its orientation. Unlike the neatly aligned disks often found around single stars, this one appears to be dramatically warped. Imagine a vinyl record bent into a bowl-like shape, its edges tilted at odd angles, and you'll get a sense of how chaotic this environment can be. This distortion is thought to be the result of gravitational interactions between the two binary pairs, tugging at the disk and warping its structure over time. The implications of this warped disk extend far beyond HD 98800. In single-star systems, protoplanetary disks are the birthplaces of planets, where clumps of material gradually coalesce into worlds. But in multi-star systems like this one, the constant gravitational pushes and pulls create a far more complex and dynamic environment. This raises important questions about how planets might form or even survive in such conditions. Could a planet emerge from such a disrupted disk? If so, what might its orbit look like? These are the kinds of puzzles that HD 98800 forces us to grapple with, challenging our understanding of planetary formation in the cosmos. What's particularly fascinating is how this system allows scientists to test theories about disk dynamics in real time. By observing the interactions between the stars and the disk, researchers can refine their models of how gas and dust behave under the influence of multiple gravitational forces. These insights don't just apply to quadruple star systems, they also shed light on other multi-star environments, helping us understand the broader role these systems play in shaping the universe. As we marvel at the complexity of HD 98800, it becomes clear that these stellar quartets are far more than just cosmic oddities. They are natural laboratories where the forces of gravity, motion, and matter collide in ways that continue to surprise and inspire. And speaking of surprises, our next discovery will take us even further into the depths of these systems, focusing on a phenomenon where appearances can be deceiving. Stay tuned as we uncover cases where quadruple systems have been mistaken for something far simpler. In our journey through the cosmos, it's time to uncover a revelation that highlights just how deceptive appearances can be. Picture this: you're peering through a telescope, confident that you've identified a single star or perhaps a simple binary system. But hidden within the flicker of light lies something far more intricate. Sometimes, even a quadruple system has been masquerading as something simpler. This is the phenomenon at the heart of our 11th discovery: visual binaries that astronomers once mistook for lone stars or binary pairs. For centuries, the tools available to study celestial objects were limited. Early astronomers relied on relatively low-resolution instruments and, at times, the unaided eye to catalog stars. Because of this, distant and complex systems often appeared as singular points of light. Even as telescopes improved, many quadruple systems, where 4 stars orbit one another in a carefully choreographed gravitational ballet, remained indistinguishable from simpler configurations. One such example is the system Capella, long believed to be a solitary star or a binary system. It wasn't until later observations with advanced technology that astronomers realized Capella is actually a quadruple system with 2 pairs of stars orbiting a common center of mass. This misidentification underscores the challenges of observational astronomy and how our understanding evolves with better tools. The difficulty arises because the stars in quadruple systems often orbit at vast distances from one another, making their light blend together when viewed from Earth. In other cases, some members of the system are so faint compared to their brighter companions that they're effectively invisible to older detection methods. It's only through modern techniques like spectroscopy, an approach that analyzes the light emitted by stars, that we've been able to separate the subtle signatures of multiple stellar bodies. These advancements have unveiled not only Capella but also other systems once thought to be simpler than they truly are. This discovery serves as a humbling reminder of how much there is to learn about the universe. It also emphasizes the importance of questioning initial assumptions. After all, what looks like a single star from afar might hide a whole family of stars locked in a gravitational embrace. As we continue to refine our tools and methods, who knows what other hidden wonders might come to light? Up next, we'll explore how these tightly knit systems can influence the very life cycles of their stellar members, revealing even more about the dynamic dance of quadruple star systems. As we shift our gaze to the intricate lives of stars, we arrive at a fascinating aspect of quadruple systems: their ability to alter the aging process of their stellar members. Imagine a cosmic dance where the participants don't just move in harmony but also influence each other's lifespans. In quadruple star systems, the close interactions between stars can lead to accelerated aging, a phenomenon that offers deep insights into stellar evolution. Stars in these systems often exist in proximity, close enough for their gravitational pull to create significant effects. When stars orbit one another at such close distances, they can exchange mass, energy, and even material from their outer layers. This interaction can dramatically alter the life cycle of a star. For instance, if one star begins to expand into its red giant phase, it might transfer some of its mass to a companion star. This influx of material can cause the receiving star to burn through its fuel more quickly, aging faster than it would in isolation. It's a bit like sharing too much of a resource. Sometimes the effect isn't just beneficial, it can push a star toward an early demise. Take the example of a system where 2 pairs of stars orbit a common center. If one of the stars in a pair loses mass to its companion, this not only accelerates the aging process but can also trigger dramatic events like nova or even supernova. These explosions, in turn, can impact the entire system, influencing the trajectories and evolution of the other stars. The process is a stunning reminder of how interconnected these stellar families truly are. Interestingly, this accelerated aging isn't just limited to 2 stars interacting closely. Even in wider quadruple systems, where stars might seem distant from one another, subtle gravitational effects can still play a role. Over time, these small interactions accumulate, leading to changes in spin rates, magnetic fields, and internal structures of the stars. Such effects are incredibly challenging to observe directly, but computer simulations and theoretical models have helped astronomers piece together these complex dynamics. This discovery challenges our traditional understanding of stellar lifespans, which are typically calculated based on isolated stars. In quadruple systems, the rules change, and what we once thought was a predictable process becomes far more dynamic and unpredictable. It's a reminder of just how much we still have to learn about the universe and how even seemingly stable systems can hold surprises. As we reflect on how these stars age and evolve together, it sets the stage for our next revelation, a puzzle that revisits a classic paradox in astronomy. How does mass transfer and tidal forces in quadruple systems tie back to the famous algol paradox? Let's unravel this mystery together. Moving from the aging processes in quadruple star systems, we now turn our attention to a classic puzzle that takes on new dimensions when viewed through the lens of these complex systems. The algol paradox has fascinated astronomers for decades, and its connection to quadruple systems adds another layer of intrigue to our cosmic journey. The algol paradox refers to a curious situation where a star in a binary system appears to be older than its companion, despite being the more massive of the two. Normally, more massive stars burn through their fuel faster and should evolve into their red giant phase before their less massive counterparts. Yet in the algol system, the opposite is observed. The smaller star has already gone through its red giant phase while the larger star still burns steadily. This reversal of roles was eventually explained through mass transfer. In these systems, the larger star donates mass to its companion, allowing the smaller star to evolve more quickly, essentially aging it prematurely. Now, when we bring quadruple star systems into the picture, this paradox becomes even more fascinating. Imagine not just two stars, but four stars, all interacting in ways that amplify the effects of mass transfer and tidal forces. Picture two pairs of stars orbiting a common center, with each pair influencing the other's evolution. If one star in a pair transfers mass to its companion, the effects can ripple outward, affecting the dynamics of the entire system. For instance, a sudden influx of mass into one binary pair could destabilize their orbits, which then creates gravitational disturbances for the other pair. This interconnected dance means that the algol paradox isn't just about two stars anymore. It's about how the aging process plays out across an entire family of stars. Tidal forces add another element to this puzzle. In quadruple systems, these forces are particularly intense because the stars are often close enough to exert significant gravitational pull on one another. These forces can stretch and distort the shapes of the stars, altering their internal structures and spin rates. Over time, this can lead to even more dramatic mass transfer events, further complicating the evolutionary timeline of the system. For example, a star that might have lived peacefully for millions of years could suddenly find itself losing mass at an accelerated rate due to the combined influence of its companion and the gravitational tug from the other binary pair. What makes this so compelling is that quadruple systems provide a natural laboratory for studying the algol paradox in action. Astronomers have long relied on binary systems to understand stellar evolution, but quadruples take these observations to a whole new level. By observing these systems over time, scientists can witness how mass and energy flow between multiple stars, reshaping their destinies. These observations challenge and refine existing models, helping us better understand the delicate balance between chaos and stability in the universe. This deeper look at the algol paradox within quadruple systems reminds us that the universe is far from a static place. Every interaction, no matter how small, can set off a chain reaction that alters the course of stellar evolution. It's a vivid illustration of how interconnected even the most distant stars can be. And as we marvel at these revelations, it naturally leads us to wonder, what role do magnetic fields play in these close-knit quadruple systems, and how do they shape the environment around these dynamic stars? Let's uncover that next. As we shift our focus to yet another captivating discovery, let's turn our attention to a system that showcases one of the universe's most intricate performances, TSC 1729-00988. This quadruple star system offers a front-row seat to a celestial ballet, where mutual eclipses between its stars create a stunning display of light and shadow. TSC 1729-00988 is unique because it allows astronomers to observe mutual eclipses, a phenomenon where stars in the system periodically pass in front of one another from our perspective. These eclipses aren't just visually fascinating, they're also packed with valuable information. When one star blocks another, it temporarily dims the system's overall light. By carefully analyzing these dips in brightness, scientists can determine the sizes, orbital paths, and even the masses of the stars involved. It's like solving a cosmic puzzle piece by piece. What makes this system particularly intriguing is the precision with which these eclipses occur. In TIC 1729-00988, two pairs of stars orbit each other in a tightly choreographed dance. One pair, consisting of two stars locked in a close embrace, orbits a second binary pair further out. Every so often, the orbital planes align just right, and we're treated to a series of mutual eclipses. These events reveal the delicate balance of forces at play: gravity, orbital dynamics, and timing, all working together to create this rare spectacle. Imagine the complexity of such a system. Each star tugs on the others, their movements influenced by the gravitational pull of their companions. Over time, these interactions can lead to subtle changes in their orbits. For example, one star might inch closer to its partner, increasing the frequency or duration of the eclipses. By tracking these changes, astronomers can study how quadruple systems evolve over time. It's a bit like watching a slow-motion dance where every step matters, but the insights don't stop there. Mutual eclipses also provide a unique opportunity to probe the properties of the stars themselves. For instance, when one star passes in front of another, the light that filters through its atmosphere can reveal details about its composition and temperature. Think of it as shining a light through a stained glass window. The colors and patterns you see tell a story about the glass itself. Similarly, the light we observe during an eclipse tells us about the star's inner workings. What's even more remarkable is how this system challenges our understanding of stability in multi-star environments. In a quadruple system like TIC 1729-00988, the potential for chaos is high. Yet, despite the gravitational tugs and pulls, the system manages to maintain a delicate equilibrium. This balance offers clues about the underlying physics that govern these complex systems, helping us refine our models of stellar dynamics. As we marvel at the intricate choreography of TIC 1729-00988, it's hard not to wonder what other hidden wonders might we uncover as we continue to explore the mysteries of quadruple star systems. Perhaps the answers lie in the next discovery, where high-energy phenomena like flares and X-ray emissions reveal even more about these stellar enigmas. Stay with us as we dive deeper into the cosmos, uncovering secrets that stretch the boundaries of our understanding. Now, let's turn our gaze to a phenomenon that lights up the cosmos in ways both dazzling and mysterious: high-energy outbursts. These explosive events, often seen as stellar flares and bursts of X-ray emissions, offer a dynamic glimpse into the inner workings of quadruple star systems. Far from being random, these outbursts are deeply tied to the activity cycles of the stars themselves, revealing hidden aspects of their behavior and interactions. In quadruple star systems, the stars aren't just passive points of light, they're dynamic and often volatile entities. Flares occur when magnetic energy stored in a star's atmosphere is suddenly released, creating a surge of radiation across the electromagnetic spectrum. Imagine a massive solar flare on our own sun, but now multiply that by 4 stars, each with its own magnetic field, and you begin to grasp the sheer energy at play here. These flares can be thousands of times more powerful than anything we've observed on our sun, temporarily bathing the system in intense radiation. What makes these high-energy outbursts even more fascinating is their connection to X-ray emissions. X-rays, a form of high-energy light invisible to the naked eye, often accompany these flares. In quadruple systems, the close proximity of stars to one another can amplify these emissions as their magnetic fields interact in unexpected ways. These interactions create what scientists call magnetic reconnection events, where magnetic field lines snap and reconnect, releasing tremendous amounts of energy in the process. This energy heats up surrounding plasma to millions of degrees, causing it to glow brightly in X-rays. But why does this matter? For one, these outbursts help us understand the life cycles of stars in multi-star systems. Stars in quadruple systems often spin faster due to the gravitational influence of their companions, which can intensify their magnetic activity. This heightened activity leads to more frequent and intense flares. By studying these outbursts, astronomers can gain insights into how stars evolve in such crowded environments, where the tug-of-war between gravity and magnetism shapes their behavior over millions of years. And there's another layer to this cosmic drama. High-energy phenomena can also impact any planets orbiting within or near the quadruple system. Imagine a world bathed in the constant glow of stellar flares, where the chances of life as we know it are drastically altered. These flares could strip away a planet's atmosphere or bombard its surface with harmful radiation, posing significant challenges for habitability. Yet, they might also provide clues about the resilience of life in extreme conditions, pushing the boundaries of astrobiology. As we explore these high-energy outbursts, we're reminded of just how interconnected the universe is. Every flare, every burst of X-rays tells a story not just about the stars themselves, but about the forces that govern their interactions. And while we've uncovered much about these explosive events, there's still so much more to learn. What other secrets lie hidden in the radiation pouring out of these systems? Perhaps the next discovery will bring us closer to understanding the delicate balance between chaos and stability in quadruple star systems. Stay tuned because the journey is far from over. As we shift our focus to the intricate dance of celestial mechanics, one of the most fascinating phenomena in quadruple star systems comes into view: orbital resonance. This is where the motions of stars are linked in a rhythmic gravitational waltz, creating patterns that can either hold these systems together or, paradoxically, tear them apart. Picture a cosmic symphony where the timing of each star's orbit syncs up in ways that echo across the system. These resonances occur when the orbital periods of stars relate to one another in simple whole number ratios like 2:1 or 3:2. In quadruple systems, orbital resonance can play a dual role. On one hand, it can act as a stabilizing force. When stars settle into these resonant patterns, their mutual gravitational tugs can cancel out over time, allowing the system to maintain a delicate balance. This is akin to a clockwork mechanism where every gear meshes perfectly, preventing chaos. But on the other hand, if the resonance becomes too strong or shifts out of alignment, it can wreak havoc. Stars might be pushed into tighter orbits or, in some cases, flung out of the system altogether. This tug-of-war between stability and instability is a key factor shaping the long-term fate of quadruple systems. What makes orbital resonance even more intriguing is its potential to shape the behavior of planets within these systems. If a planet happens to orbit near one of these resonances, its path could be subtly altered over time. For example, a planet caught in a resonant interaction might experience periodic nudges, causing its orbit to stretch into an ellipse. Over millions of years, this could lead to dramatic changes in the planet's climate or even its habitability. Imagine a world where every few centuries, its distance from its host stars shifts just enough to trigger a freeze or a thaw, a cosmic pendulum swinging to the rhythm of gravity. But these resonances don't just affect individual orbits, they can influence the system as a whole. In some cases, the gravitational interactions can cascade through the quadruple system, redistributing energy in ways that reshape entire configurations. This might explain why some quadruple systems seem to defy expectations, persisting for billions of years despite their inherent complexity. It's a reminder that even in the most chaotic environments, there's often an underlying order waiting to be uncovered. And yet, for all we've learned about orbital resonances, they remain one of the great unsolved puzzles in the study of multi-star systems. How do these resonances form in the first place? What determines whether they stabilize or destabilize a system? The answers to these questions could hold the key to understanding not just quadruple star systems, but the fundamental laws that govern the motion of celestial bodies. As we continue our journey through these cosmic mysteries, keep in mind that the same forces shaping these distant stars might also offer insights closer to home, like the dynamics of moons around planets or even the behavior of galaxies. Let's now turn our attention to another enigmatic aspect of quadruple systems, their potential to emit gravitational waves, a discovery that could transform our understanding of the universe. Stay with us as we explore this thrilling possibility. Stepping into the realm of the unseen yet profoundly influential, we arrive at a groundbreaking prediction: the gravitational wave signatures of quadruple star systems. These systems, with their intricate dances and powerful gravitational interactions, could be cosmic beacons for one of the most elusive phenomena in modern astronomy: gravitational waves. While we've long associated these ripples in space-time with cataclysmic events like black hole mergers or neutron star collisions, quadruple systems bring a new dimension to the story. Their complex orbital dynamics may produce unique wave patterns that could one day be detected by our ever-advancing observatories. Gravitational waves are essentially ripples in the fabric of space-time, generated when massive objects accelerate or change their configuration. In a quadruple star system, the constant shifting of 4 stars around one another creates a chaotic yet rhythmic interplay of gravitational forces. These forces, especially when stars pass close to each other or when their orbits become highly elliptical, can generate waves that propagate outward at the speed of light. The challenge lies in distinguishing these waves from the background noise of the universe, but theorists are optimistic. They suggest that certain configurations, particularly those with tightly packed orbits or extreme mass ratios, might produce signatures distinct enough to stand out. What makes these theoretical predictions so exciting is their potential to open a new window into the universe. Imagine being able to detect and study a quadruple system not by the light it emits, but by the subtle distortions it imprints on space-time itself. This would allow astronomers to probe systems that are otherwise too distant or obscured by dust and gas. For instance, a quadruple system deep within the Milky Way or even in a neighboring galaxy might reveal its secrets through the gravitational waves it sends rippling across the cosmos. These waves could tell us about the masses of the stars, their orbital periods, and even the history of their interactions, details that are often difficult to glean through traditional observations. But the implications go even further. Detecting gravitational waves from quadruple systems could provide a unique test for Einstein's general theory of relativity. This theory predicts that gravitational waves carry energy away from a system, causing orbits to gradually shrink over time. In quadruple systems where multiple gravitational forces are at play, the effects could be amplified, offering a clearer signal for scientists to study. Moreover, if quadruple systems are found to host compact objects like neutron stars or black holes, the resulting waves could be even more pronounced, offering a treasure trove of data for researchers. While we are still in the early stages of this exploration, the prospect of detecting these waves is closer than ever. Facilities like LIGO and Virgo have already made incredible strides in observing gravitational waves from simpler systems, and future observatories, such as the space-based LISA mission, are designed to detect lower frequency waves that might originate from quadruple systems. These advancements could transform our understanding of not just quadruple stars, but also the fundamental nature of gravity itself. As we look to the future, the detection of gravitational waves from these systems might not just be a possibility. It could become a reality that reshapes how we view the universe. With this intriguing glimpse into the potential of gravitational wave astronomy, we're reminded of the countless mysteries still waiting to be uncovered. And speaking of mysteries, our next discovery takes us into the realm of how these systems are named, adding a touch of light-hearted intrigue to the cosmic puzzle. Stay tuned as we unravel the nuances of naming conventions in quadruple star systems. Now that we've explored the profound mysteries of gravitational waves, let's take a moment to appreciate something a little closer to home: how astronomers keep track of the stars themselves. Naming conventions might not sound as exciting as cosmic ripples, but trust me, it's a topic full of quirks and charm. After all, when you're dealing with 4 stars instead of 1, keeping everything straight becomes an art form in itself. In quadruple star systems, each star is typically labeled with a combination of letters and sometimes numbers, following a system that astronomers have refined over centuries. The primary star, often the brightest or most massive, is given the designation A. From there, things get interesting. The next star in the system is labeled B, and if there are additional components, they're named C and D. It's straightforward enough, but what happens when those stars themselves have companions? That's where the fun begins. Take, for example, a system where one of the stars is actually a binary pair. Instead of simply being called B, the 2 stars in that binary would be labeled Bar and BB. If one of those stars happens to be part of another binary, the naming gets even more intricate with labels like Bar or Bab. It might sound like alphabet soup, but this hierarchical approach ensures that every star has its place in the cosmic family tree. It's a system that's both practical and oddly poetic, reflecting the complex relationships between these celestial bodies. But it's not just about letters and numbers. Some quadruple systems have earned nicknames based on their appearance or behavior. For instance, a system where the stars align in a particularly striking way might be given a moniker inspired by mythology or folklore. These names add a human touch to the otherwise technical labels, bridging the gap between science and storytelling. It's a reminder that even in the vastness of space, we can't help but bring a little creativity into the mix. Interestingly, naming conventions can also reveal a lot about how astronomers view these systems. The use of hierarchical labels underscores the importance of understanding the gravitational relationships between the stars. By organizing the system into primary, secondary, and tertiary components, researchers can better predict how the stars might interact over time. It's like creating a roadmap for the stars, one that helps guide both observation and theory. Of course, not all naming conventions are universally loved. Some astronomers argue that the current system can become overly complicated, especially for systems with more than 4 stars. Imagine trying to keep track of EB2 or FAC1b. It's enough to make anyone's head spin. As a result, there's ongoing discussion about how to simplify or standardize the process, ensuring that the names remain useful without becoming a headache. As we marvel at these naming quirks, it's worth noting that they highlight an important truth about astronomy. Even the smallest details matter. Whether it's the way we label stars or the way we interpret their movements, every piece of information adds to the larger puzzle of understanding the universe. And speaking of details, our next discovery takes us into the fascinating world of photometric variability studies, where even the faintest flickers of light can reveal hidden secrets about quadruple systems. Stay with us as we uncover how astronomers use these subtle changes to shine a light on the cosmos. Moving from the art of naming stars to the science of observing their behavior, we arrive at a tool that has revolutionized our understanding of celestial systems: photometric variability studies. This method might sound technical, but at its core, it's about watching how stars change in brightness over time. These changes, often subtle and easy to miss, can reveal the presence of not just one star, but entire systems hiding in plain sight. Photometric variability studies work by measuring the light emitted by stars with incredible precision. When a star's brightness dips or fluctuates, it's often a sign that something is passing in front of it, or that its light is being influenced by another object. In quadruple star systems, this is especially valuable. Imagine a scenario where two stars in the system are so close to each other that they appear as a single point of light from Earth. By carefully analyzing changes in brightness, astronomers can detect the presence of these hidden companions, piecing together the true structure of the system. What makes this technique truly remarkable is its ability to uncover systems that might otherwise remain invisible. Some quadruple star systems are so distant or faint that traditional methods of observation struggle to resolve their individual components. But photometric variability studies don't rely on directly seeing the stars. They rely on interpreting their effects on light. This makes the method an essential tool for probing the depths of space. Take, for example, systems where one star periodically eclipses another. These eclipsing binaries are a goldmine for researchers because the timing and duration of the eclipses can provide precise data about the star's sizes, masses, and orbits. When these eclipses occur within quadruple systems, the complexity increases, but so does the opportunity for discovery. By untangling the light curves, astronomers can map out the intricate dance of four stars, understanding not just their positions but also their interactions. It's not just eclipses that these studies can reveal. Stars in quadruple systems often experience fluctuations in brightness due to other factors, like pulsations or magnetic activity. These variations add layers of information, helping scientists build a more complete picture of the system's dynamics. In some cases, the data even hints at the presence of planets or dust disks, further enriching our understanding of these cosmic neighborhoods. Of course, photometric variability studies aren't without their challenges. The data can be noisy, and teasing out meaningful patterns requires sophisticated algorithms and a lot of patience. But the rewards are well worth the effort. Every dip in brightness, every unexpected flicker of light, brings us closer to uncovering the hidden architectures of the universe. As we marvel at the power of light to reveal the unseen, it's time to shift our focus to another fascinating aspect of quadruple star systems, the role of tidal forces. These forces, which shape the orbits and even the internal structures of stars, hold the key to understanding how these systems maintain their delicate balance. Join us as we dive deeper into this gravitational tug-of-war and explore the dynamic forces at play. Let's now turn our attention to the invisible hands that sculpt the motion of stars, the tidal forces at play within quadruple systems. These forces, though unseen, wield incredible power, shaping how stars move, spin, and even evolve over time. To understand their role, we need to first grasp what tidal forces are. Imagine the tug-of-war between two stars as they orbit each other. The gravitational pull is stronger on the side of each star that faces its companion, creating a stretching effect. This is tidal force in action, and in quadruple systems, it becomes a complex dance involving multiple players. In these systems, tidal forces don't just affect individual stars, they influence the entire structure of the system. For instance, when two pairs of stars orbit a common center of mass, their gravitational interactions can cause the stars to gradually synchronize their spins with their orbits. This phenomenon, known as spin-orbit alignment, occurs because the tides act like a brake, slowing down or speeding up the rotation of the stars until they match the orbital rhythm. Over time, this synchronization can lead to a more stable configuration, helping these intricate systems endure despite their chaotic nature. But tidal forces don't stop there. They also play a key role in something called orbital decay, where the distance between stars in a binary pair or even between the two pairs in a quadruple system slowly decreases. This happens because the gravitational tugging generates energy that gets radiated away, often in the form of gravitational waves. While this process is subtle and occurs over millions or billions of years, its effects are profound. In some cases, orbital decay can bring stars so close together that they merge, creating new types of celestial objects or even triggering explosive events like supernova. What makes tidal forces truly fascinating is their ability to influence not just the stars, but also any planets or disks of material within the system. For example, if a planet orbits close to one of the stars, the same tidal interactions that shape the stars can also affect the planet's orbit, potentially pulling it closer or even ejecting it from the system entirely. This adds another layer of complexity to the already intricate dynamics of quadruple systems. Understanding these forces gives us a glimpse into the delicate balancing act that keeps quadruple systems from flying apart. Yet, tidal forces are just one piece of the puzzle. As we explore further, we uncover another peculiar aspect of these systems: their unusual chemical compositions. These cosmic oddities hint at exotic formation pathways and offer clues about the environments in which these systems were born. Stay with us as we unravel the secrets hidden within the star's very makeup. Now, let's shift our gaze to something truly out of the ordinary: the peculiar chemical fingerprints of stars within quadruple systems. These celestial bodies often reveal compositions that defy the norm, offering a cosmic puzzle that astronomers are eager to solve. To understand why this matters, we need to first consider what makes a star's chemistry unusual. Typically, stars are made up of hydrogen and helium, with trace amounts of heavier elements like carbon, oxygen, and iron. But in quadruple systems, some stars display surprising abundances of these heavier elements, or conversely, a striking lack of them. Take, for instance, the phenomenon of metal-rich stars. In these cases, the stars contain a higher concentration of elements heavier than helium, referred to as metals in astronomical terms. This could suggest that these stars formed in regions of space where such elements were more abundant, perhaps due to the remnants of previous stellar explosions enriching the surrounding gas clouds. On the flip side, some quadruple systems host stars that are unusually metal-poor, meaning they lack these heavier elements. This might hint at a very different origin, possibly in regions of space where the raw materials for star formation were less processed. What makes these chemical quirks even more intriguing is their potential connection to the formation of quadruple systems themselves. One theory is that the unusual compositions could result from interactions between the stars during their early years. Picture this: in the chaotic early stages of a quadruple system's life, stars might exchange material or even strip away layers from one another. This process could leave behind stars with altered chemical compositions, like fingerprints that tell the story of their turbulent past. But the mystery doesn't stop there. Some of these chemical signatures might also point to the influence of external factors, like nearby supernova or encounters with passing stars. For example, if a massive star in the vicinity exploded as a supernova, the blast could have scattered heavy elements into the gas cloud from which the quadruple system formed. This would leave an indelible mark on the chemical makeup of the stars, like a cosmic signature etched into their very cores. These unusual compositions also raise questions about the environments in which quadruple systems are born. Were they forged in dense star clusters where frequent interactions with neighboring stars could alter their chemistry? Or did they form in relative isolation, shaped by internal dynamics alone? By studying the chemical compositions of these stars, scientists hope to piece together the conditions of their birthplaces and uncover the exotic pathways that led to their formation. As we move forward, we'll explore another rare and captivating phenomenon: alignments within quadruple systems where three stars appear nearly collinear. These fleeting moments of celestial symmetry offer stunning visual effects and provide a unique opportunity to study the intricate gravitational relationships at play. Stay tuned as we continue to unravel the secrets of these cosmic wonders. Now, let's turn our attention to a breathtaking phenomenon that occurs within some quadruple star systems: triple star alignments. These rare and fleeting moments happen when three of the stars in the system appear almost perfectly lined up from our perspective here on Earth. This celestial ballet creates a stunning visual effect, one that captures the imagination of astronomers and stargazers alike. Imagine looking through a telescope and seeing three glowing orbs stacked neatly, like beads on a cosmic string. The alignment doesn't last long, as the stars are constantly moving in their complex orbital dances, but when it does happen, it provides a unique opportunity to study their gravitational interactions. These alignments are more than just a pretty sight. They offer clues about the intricate relationships between the stars in the system. For example, when three stars align, their combined light can temporarily brighten the system, creating what astronomers call a syzygy event. This term might sound exotic, but it simply refers to a straight-line configuration of three celestial bodies. During these events, scientists can gather valuable data about the stars' sizes, temperatures, and even their atmospheres. By analyzing the way light changes as the stars pass near each other, researchers can better understand how these systems maintain their delicate balance. But what makes these alignments so rare? Well, quadruple systems are already complex, with 4 stars orbiting in a hierarchical structure. For 3 of them to line up in just the right way requires very specific conditions. The stars must be at particular points in their orbits, and their paths must be oriented favorably from our vantage point. It's like trying to catch a needle in a haystack, but when it happens, it's nothing short of magical. These alignments also have practical applications beyond their beauty. They can help astronomers refine models of gravitational dynamics within quadruple systems. By studying how the stars influence each other during these moments, researchers can test theories about orbital stability and energy exchange. This, in turn, sheds light on how these systems evolve over time and how likely they are to remain intact or eventually break apart. As we marvel at these celestial alignments, it's worth considering how they fit into the larger puzzle of quadruple star systems. They remind us that even in the vastness of space, there are moments of perfect symmetry, fleeting though they may be. And speaking of rare occurrences, our next discovery takes us to a perplexing mystery, cases where quadruple systems seem to lose members. Let's explore how and why this happens, and what it tells us about the dynamic nature of these stellar families. Now, let's unravel a cosmic mystery that has puzzled astronomers for years: the curious case of missing members in quadruple star systems. It's a phenomenon that sounds almost like a celestial whodunit. How does a system that starts with 4 stars end up with fewer, and where do these missing stars go? In some quadruple systems, astronomers have observed that 1 or more stars seem to vanish over time. But stars don't just disappear, they must be leaving the system entirely. This process is known as ejection, and it's a dramatic event driven by the intricate gravitational interactions within these star families. Think of it like a cosmic tug of war, where the balance shifts so drastically that one star gets flung out into the vastness of space. So, what causes these ejections? One possibility lies in the hierarchical structure of quadruple systems. These systems often consist of 2 pairs of stars orbiting each other, but when the gravitational forces between the pairs become unstable, chaos can ensue. A close encounter between the 2 binary pairs might give one star a gravitational kick, accelerating it to such high speeds that it escapes the pull of the system entirely. Imagine a crowded dance floor where one dancer suddenly spins out of control and shoots off into the night. Only in this case, the dancer is a massive star hurtling through the galaxy. Another scenario involves a supernova explosion within the system. If one of the stars reaches the end of its life and explodes, the sudden loss of mass can disrupt the delicate balance holding the system together. The explosion might propel 1 or more companion stars out into space, leaving behind a smaller, less populated system, or sometimes no system at all. What's fascinating is that these ejected stars don't just vanish, they become rogue stars wandering the galaxy without a stellar companion. Some of these rogue stars might even carry planets with them, creating an entirely new class of wandering worlds. This raises intriguing questions about the long-term stability of quadruple systems. Are these ejections a common outcome, or are they rare events that only happen under very specific conditions? To answer this, astronomers study the trajectories and velocities of stars in nearby systems, looking for signs of past ejections. They also run computer simulations to model how different configurations of quadruple systems might evolve over millions or billions of years. These simulations suggest that while some systems remain stable for eons, others are inherently chaotic, destined to lose members sooner or later. But the mystery doesn't end there. What happens to the stars left behind after an ejection? The sudden loss of a member can drastically alter the dynamics of the remaining system. The gravitational forces that once kept everything in balance might now cause the remaining stars to drift apart or even collide. And what about the ejected star itself? Once cast out, it embarks on a solitary journey through the galaxy, its fate tied to the whims of gravity and chance encounters with other celestial bodies. As we ponder these questions, it's clear that the mystery of missing members in quadruple star systems is far from solved. Yet, each new discovery brings us closer to understanding the delicate interplay of forces that govern these stellar families. And speaking of forces, our next discovery explores how external influences like passing stars or galactic tides can further shape the destiny of these complex systems. Let's dive into how these outside factors can tip the scales in the already precarious balance of quadruple star systems. Shifting our gaze from the external forces that disrupt quadruple star systems, let's now focus on the tools astronomers use to uncover their secrets. One of the most groundbreaking advancements in studying these intricate systems is interferometry. This technique has revolutionized our ability to peer into the heart of quadruple star systems, revealing details that were once beyond our reach. Interferometry works by combining the light collected from multiple telescopes, effectively creating a virtual telescope as large as the distance between them. This allows astronomers to achieve an incredible level of resolution, far greater than what any single telescope could provide. Think of it like using multiple eyes to see the same object from slightly different angles, giving a much sharper and more detailed picture. For quadruple star systems, which are often so distant that their individual stars appear blurred together, this precision is nothing short of transformative. Take, for instance, the system known as Capella. Observations using interferometry revealed that what was once thought to be a simple binary system is actually a quadruple system. By carefully analyzing the light patterns, astronomers identified two pairs of stars orbiting each other in a delicate cosmic dance. This discovery not only expanded our understanding of Capella, but also highlighted the potential of interferometry to rewrite what we know about stellar configurations. What makes interferometry particularly powerful is its ability to measure the positions and movements of stars with astonishing accuracy. In quadruple systems, where the gravitational interactions are complex and constantly shifting, this precision is crucial. It allows scientists to track the orbits of individual stars, study their masses, and even detect subtle changes over time. These insights help us piece together the history and future of these systems, offering clues about how they formed and how they might evolve. Beyond resolving individual stars, interferometry has also shed light on the environments surrounding quadruple systems. For example, it has helped map dust disks and gas clouds that often accompany these systems. These structures are key to understanding how stars and planets form, as they contain the raw materials needed to build new worlds. By studying them, astronomers gain a deeper appreciation for the interconnected processes that shape the universe. Yet, despite its power, interferometry is not without its challenges. The technique requires extremely precise alignment of telescopes and sophisticated data processing to combine the light signals effectively. Weather conditions, atmospheric turbulence, and even the Earth's rotation can all interfere with observations. However, recent advancements in technology have made interferometry more reliable and accessible, opening up new possibilities for exploring quadruple systems in greater detail than ever before. As we celebrate the role of interferometry in unraveling the mysteries of quadruple star systems, it's worth noting how this tool connects to our next discovery. Understanding the distribution of orbital inclinations in these systems gives us further insight into their origins and evolution. With sharper observations and better data, we're one step closer to answering some of the universe's most intriguing questions. So let's delve into the puzzle of orbital inclinations and see what secrets they hold. As we peel back another layer of the cosmic onion, let's turn our attention to a factor that quietly shapes the universe's metallicity. You might be wondering, what exactly is metallicity? In simple terms, it refers to the amount of elements heavier than hydrogen and helium present in a star. These elements, which astronomers collectively call metals, play a surprisingly crucial role in the formation and behavior of star systems, including quadruple ones. So, how does metallicity influence these complex systems? Let's find out. To understand this, imagine a bustling stellar nursery where new stars are born from vast clouds of gas and dust. The composition of these clouds, particularly their metallicity, dictates how efficiently stars can form and how stable their resulting systems will be. In environments with higher metallicity, the abundance of heavier elements helps gas clouds cool down more effectively. This cooling process allows the clouds to collapse more easily, forming stars with greater efficiency. As a result, quadruple star systems are more likely to emerge in regions of the galaxy where metallicity is relatively high. But metallicity doesn't just affect the birth of these systems, it also has a say in their long-term stability. Quadruple star systems are like delicate clockwork, with each star influencing the others through gravitational tugs and orbital dynamics. The presence of heavier elements can impact the masses and sizes of the stars, which in turn affects their gravitational interactions. Systems born in low metallicity environments might struggle to maintain stability, as their stars could be too massive or too close together, leading to chaotic and potentially short-lived configurations. On the flip side, systems with just the right balance of metals can achieve a harmonious dance, where their orbits remain stable over millions or even billions of years. Interestingly, metallicity also ties into the types of stars we find in quadruple systems. Stars with higher metallicity are often cooler and redder, while those with lower metallicity tend to burn hotter and bluer. This difference can influence how these systems appear to us from Earth and how they evolve over time. For example, quadruple systems with lower metallicity might host stars that burn through their fuel more quickly, leading to dramatic events like supernova. These explosive endings can reshape the surrounding space, scattering heavy elements that might one day contribute to the formation of new stars and planets. Now, you might be wondering, does this mean quadruple systems are more common in certain parts of the galaxy? The answer is yes. Regions like the galactic disk, where metallicity tends to be higher, are hotspots for these intricate systems. In contrast, the outer reaches of the galaxy, where metallicity is lower, see far fewer quadruple systems. This distribution gives us important clues about the conditions that favor their formation and persistence. As we reflect on the role of metallicity in shaping quadruple star systems, it's hard not to marvel at the delicate interplay between chemistry and physics on a cosmic scale. But there's another intriguing aspect to consider: how external factors like passing stars or galactic tides can disrupt these systems regardless of their metallicity. This brings us to our next discovery, where we'll explore how these external perturbations influence the dynamics of quadruple star systems. Stay tuned, because the universe is about to get even more fascinating. Shifting our gaze to a truly mind-bending phenomenon, let's explore the extraordinary world of extreme mass ratios in quadruple star systems. These systems are like cosmic oddities, where the stars involved are so vastly different in size and mass that they challenge everything we think we know about stellar physics. Picture this: one star in the system might be hundreds of times more massive than another, creating a gravitational tug of war that seems almost impossible to sustain. These extreme mass ratios occur when a star with an enormous mass, often referred to as a supergiant, shares a system with much smaller, less massive stars, sometimes even dwarf stars. In some cases, one star could be a blazing powerhouse, radiating energy at an incredible rate, while its companion might be a faint, tiny ember by comparison. Such disparities in mass create a system that defies conventional expectations, forcing scientists to rethink how stars interact in multi-star environments. One fascinating example of this is a system where a star with a mass many times greater than our Sun coexists with a red dwarf, which might weigh in at just a fraction of the Sun's mass. The gravitational influence of the larger star dominates the system, but the smaller star still plays a critical role. It acts like a cosmic counterbalance, subtly influencing the motions of the more massive star and contributing to the stability or instability of the system. This delicate interplay raises questions about how these systems form in the first place and how they manage to survive over time. What makes these extreme mass ratios so captivating is that they push the limits of our understanding. For instance, when two stars in a quadruple system have such vastly different masses, their orbital dynamics can be wildly unpredictable. The larger star's immense gravity might cause the smaller star to whip around in a tight, high-speed orbit, while the other binary pair in the system tries to maintain its own rhythm. These interactions create a chaotic yet mesmerizing celestial dance, where the smallest gravitational nudge could send the system spiraling into disarray. But it's not just about the spectacle. Studying these systems provides invaluable insights into the fundamental principles of physics. Scientists use them as natural laboratories to test theories about gravity, orbital mechanics, and the behavior of matter under extreme conditions. In fact, observing how stars of such different masses coexist offers clues about the processes that govern star formation and evolution, helping us piece together the larger puzzle of how the universe operates. As we marvel at these extreme mass ratios, it's worth noting that these systems are not just rare curiosities. They also challenge us to expand our knowledge of the cosmos. And speaking of pushing boundaries, our next discovery takes us into the realm of ultra-compact configurations, where stars are crammed into unimaginably tight spaces, creating some of the densest star systems ever observed. Prepare to have your mind stretched even further as we delve into this extraordinary phenomenon. Now let's zoom in on a phenomenon that redefines the concept of cozy celestial neighborhoods: ultra-compact configurations in quadruple star systems. Imagine four stars packed so tightly together that their orbital spaces are comparable to the size of our solar system, or even smaller. It's like a cosmic apartment building where everyone shares the same hallway, but instead of neighbors borrowing sugar, these stars are exchanging gravitational tugs and tidal forces. In these ultra-compact systems, the distances between the stars are so minuscule that they're measured in terms of astronomical units, or even less, sometimes just a few times the radius of the stars themselves. To put this into perspective, the distance between our Sun and Earth is about 150 million kilometers, or 1 astronomical unit. In ultra-compact quadruple systems, the stars might orbit each other at distances far shorter than that, creating an environment where their gravitational interactions are extraordinarily intense. What makes these systems so fascinating is the sheer improbability of their existence. Stars are not small objects, they're massive, glowing spheres of gas, often millions of kilometers in diameter. Packing four of them into such close quarters without them colliding or merging is a cosmic miracle of sorts. Scientists believe that these systems likely form through specific scenarios, such as the remnants of a larger, unstable system that ejected some of its members, leaving behind a tightly knit quartet. One intriguing aspect of ultra-compact configurations is the orbital speeds involved. Because the stars are so close to each other, they zip around their shared center of mass at incredible velocities. Some of these stars complete an orbit in mere hours or days, an astonishing contrast to the years it takes planets like Earth to complete even a single trip around the Sun. This rapid movement creates a dynamic environment where energy is constantly being exchanged between the stars, leading to unique astrophysical phenomena. For example, tidal forces play a huge role in these systems. The gravitational pull of one star can distort the shape of another, creating what's known as tidal deformation. Over time, these forces can sap energy from the orbits, causing the stars to spiral closer together. In some cases, this process might culminate in a dramatic merger, where two stars collide to form a single, more massive star. Such events release extraordinary amounts of energy, sometimes visible as bright outbursts across the galaxy. But ultra-compact quadruple systems aren't just about spectacle, they are also treasure troves of scientific data. By studying these systems, researchers can test the limits of Einstein's theory of general relativity, which predicts how gravity behaves under extreme conditions. Observations of these tight-knit stellar clusters also provide insights into how energy and angular momentum are transferred between objects in close proximity, helping us refine our models of star formation and evolution. Another remarkable feature of ultra-compact systems is their potential to host unusual types of planets. While it might seem unlikely for planets to exist in such chaotic environments, simulations suggest that stable orbits could still form in specific regions of these systems. If such planets do exist, they would experience a sky filled with multiple suns moving in complex patterns, creating a day-night cycle unlike anything we've ever seen. As we reflect on the wonders of ultra-compact configurations, it's hard not to marvel at the delicate balance that allows these systems to exist. And yet, their very existence challenges us to think differently about the boundaries of possibility in the universe. But don't get too comfortable just yet. Our next discovery takes us into the realm of external perturbations, where even the most stable celestial systems can be thrown into chaos by forces lurking beyond their boundaries. Stay tuned to uncover how these distant influences shape the destiny of quadruple star systems. Now, let's shift our gaze outward and explore how even the most intricate cosmic dances can be disrupted by forces lurking beyond their boundaries. Imagine a quadruple star system perfectly balanced in its delicate orbits, suddenly feeling the influence of a distant passerby, a star from another region of the galaxy drifting too close, or the subtle pull of galactic tides stretching across light years. These external perturbations may seem minor at first glance, but their effects can ripple through the system, altering orbits, destabilizing configurations, and sometimes even tearing these stellar families apart. External perturbations come in many forms, but two of the most significant culprits are passing stars and the gravitational pull of the galaxy itself. When a star ventures near a quadruple system, its gravity acts like an invisible hand tugging at the stars within. Even a close encounter from hundreds of billions of kilometers away can nudge the system out of equilibrium. For quadruple star systems, which already operate on a razor's edge of stability, such disturbances can be catastrophic. Orbits that have remained steady for millions of years might suddenly become erratic, leading to chaotic interactions between the stars. Galactic tides, on the other hand, operate on a much larger scale. These tides arise because galaxies, including our Milky Way, are not uniform gravitational fields. Instead, they exert stronger gravitational forces closer to their centers and weaker forces farther out. For a quadruple star system near the edge of a galaxy, these differences in gravitational pull can stretch and distort the system over time, gradually influencing the star's movements. While the effects of galactic tides are subtle and take millions of years to manifest, they can still play a significant role in shaping the long-term fate of these systems. What makes external perturbations so fascinating is their unpredictability. Unlike the internal dynamics of a quadruple system, which can often be modeled with precision, external influences are harder to anticipate. A passing star might only nudge the system slightly, causing minor adjustments in the star's orbits, but in some cases the effects can be far more dramatic. Imagine one star being flung out of the system entirely, leaving behind a triplet that struggles to regain stability. Or picture a scenario where the perturbation forces two stars to spiral closer together, eventually merging in a fiery explosion that lights up the galaxy. Scientists study these perturbations not just to understand how quadruple systems evolve, but also to gain insights into the broader dynamics of galaxies. By observing how distant forces affect these tightly bound systems, researchers can better understand the distribution of mass in galaxies and the gravitational environments that shape stellar behavior. It's like using a cosmic microscope to study the universe on both the smallest and largest scales. Interestingly, external perturbations can also create opportunities for new discoveries. When a quadruple system is disrupted, it might eject one of its members at an incredibly high velocity, creating what astronomers call a hypervelocity star. These runaway stars can travel at speeds exceeding hundreds of kilometers per second, sometimes even escaping the galaxy entirely. Tracking these stars provides valuable clues about the environments they came from and the forces that propelled them into the void. And while external perturbations often spell chaos for quadruple star systems, they also remind us of the interconnectedness of the cosmos. No system exists in isolation. Every star, every orbit, and every gravitational interaction is part of a vast, intricate web that spans galaxies. As we continue to unravel the mysteries of these distant systems, we're left to wonder, what other forces, unseen and unknown, might be shaping the universe in ways we have yet to comprehend? Up next, we'll delve into the peculiar chemical compositions found in some quadruple systems, offering yet another piece of the cosmic puzzle. Stay with us as we uncover the unique fingerprints left behind by these stellar enigmas. Moving forward, we arrive at a captivating phenomenon that sheds light not only on the stars themselves, but also on the hidden mechanics churning deep within their cores. Pulsating stars in quadruple systems offer astronomers a rare kind of cosmic laboratory. These stars, which rhythmically expand and contract, behave like stellar heartbeats, and their oscillations carry vital clues about their internal structures. By studying these pulsations, researchers can peer beneath the surface of these distant suns, unraveling secrets that would otherwise remain concealed. So why are pulsating stars so special, especially when they're found in the complex environment of a quadruple system? To answer that, we first need to understand what causes a star to pulsate. Stars are dynamic objects, constantly balancing the inward pull of gravity against the outward pressure of energy produced in their cores. In some stars, this balance isn't perfectly stable, leading to periodic changes in their size, brightness, and temperature. These changes manifest as regular pulsations, with the star swelling and shrinking over days or even hours. The patterns of these oscillations are directly tied to the star's internal layers, making them a kind of stellar sonar that reveals what's happening deep inside. Now, when these pulsating stars are part of a quadruple system, things get even more intriguing. The gravitational pulls from their companion stars add an extra layer of complexity. Imagine a star that's already oscillating, trying to maintain its rhythm, while simultaneously being tugged in different directions by its stellar neighbors. It's like a drummer trying to keep a steady beat while being jostled by a crowd. These interactions can subtly alter the pulsation patterns, providing scientists with additional data about both the pulsating star and the system's overall dynamics. One famous type of pulsating star often found in such systems is the Cepheid variable. These stars serve as cosmic measuring sticks because their pulsation periods are directly linked to their intrinsic brightness. By observing a Cepheid in a quadruple system, astronomers can not only determine its distance but also study how its oscillations are influenced by its companions. This dual role makes Cepheids incredibly valuable for understanding both stellar physics and the architecture of multi-star systems. Another type, called hierarchical stars, pulsates much more rapidly and are often used to study older stellar populations, giving us a glimpse into the history of the universe. But it's not just about the stars themselves. The interactions within a quadruple system can also affect the pulsations in ways that mirror the system's stability or lack thereof. If the gravitational dance between the stars becomes too chaotic, it can disrupt the pulsation patterns, creating irregularities that act as warning signs of impending instability. By carefully monitoring these changes, astronomers can predict whether the system might eventually eject one of its members or even undergo a catastrophic merger. What makes this discovery particularly exciting is the way it combines two areas of astronomy, stellar oscillations and multi-star dynamics, into one unified field of study. It's like finding a key that unlocks two doors at once. Through pulsating stars, we gain insights into the inner workings of stellar bodies while also exploring the delicate gravitational choreography that governs quadruple systems. And as telescopes grow more advanced, capable of detecting even the faintest pulsations, we can expect to uncover even more about these celestial enigmas. With each pulsation, these stars whisper their secrets across light years of space, inviting us to listen closer. Yet their stories are far from complete. Up next, we'll venture into even more speculative territory as we explore the tantalizing possibility of quadruple pulsar systems, something that could redefine our understanding of extreme stellar environments. Stay tuned, because the universe has a way of surprising us when we least expect it. Stepping into the realm of the truly extraordinary, we now turn our gaze to a question that stretches the boundaries of what we know about the universe. Could there be quadruple pulsar systems hiding in the vastness of space? And if so, what could they teach us about the cosmos? Pulsars, for those unfamiliar, are incredibly dense remnants of exploded stars, spinning rapidly and emitting beams of radiation like celestial lighthouses. When found in pairs or triples, they've already proven to be invaluable for testing theories of gravity and the behavior of matter under extreme conditions. But a quadruple pulsar system, that would be a discovery of monumental proportions. The search for such a system is not just a matter of astronomical curiosity, it's a quest that could revolutionize our understanding of physics. Pulsars are already some of the most precise clocks in the universe, and their regular signals allow scientists to measure phenomena like gravitational waves and the effects of space-time curvature. Now imagine 4 of these ultra-precise cosmic clocks, all interacting with one another in the intricate gravitational ballet of a quadruple system. The data from such a configuration could provide unprecedented insights into the fundamental forces shaping the universe. So, why haven't we found one yet? The challenges are immense. Pulsars are notoriously difficult to detect because their beams must align perfectly with Earth for us to observe them. Multiply that difficulty by 4, and you begin to see why a quadruple pulsar system has eluded astronomers so far. Even if such a system exists, the chances of all 4 pulsars being oriented just right for detection are incredibly slim. But as technology advances, particularly with the advent of next-generation radio telescopes like the Square Kilometre Array, our odds are improving. What makes the prospect of a quadruple pulsar system so tantalizing is the sheer range of questions it could answer. For one, it could help us refine our understanding of gravity. Einstein's theory of general relativity has passed every test we've thrown at it, but extreme environments like those found in pulsar systems might reveal cracks in the theory we haven't yet noticed. A quadruple system would provide an even richer testing ground, allowing us to examine how gravity behaves when multiple massive objects are in close proximity, tugging and warping space-time in complex ways. Additionally, these systems might hold clues about the life cycle of stars. Pulsars are born from supernova, the explosive deaths of massive stars. Finding 4 pulsars in a single system would suggest that these stars formed together and somehow survived multiple supernova events without being torn apart. This would force us to rethink our models of stellar evolution and the conditions that allow such systems to endure. Of course, the discovery of a quadruple pulsar system would also have practical implications. Pulsar timing arrays, which use the signals from multiple pulsars to detect gravitational waves, could become exponentially more sensitive with data from such a system. This could accelerate our ability to map the universe's largest structures and even shed light on the mysterious nature of dark matter and dark energy. While we haven't found a quadruple pulsar system yet, the search itself is a reminder of how much there is still to learn. Every new observation, every faint signal detected, brings us one step closer to uncovering these potential cosmic treasures. And if history is any guide, the universe has a way of surprising us in ways we never anticipate. With that in mind, let's now turn our attention to another fascinating aspect of quadruple systems, how their rare configurations can challenge everything we thought we knew about orbital dynamics and stability. The journey continues as we shift our focus from the tantalizing possibility of quadruple pulsar systems. We journey now to the bustling neighborhoods of star clusters, where young quadruple systems offer a glimpse into the universe's formative years. Picture this: stellar nurseries teeming with activity where new stars are born in close proximity, their gravitational interactions shaping their destinies. Among these stellar infants, quadruple systems provide a unique laboratory for studying how stars grow, evolve, and interact in such crowded environments. Young quadruple systems found in star clusters are like cosmic time capsules, preserving clues about the early dynamical evolution of multiple star arrangements. These systems begin their lives embedded in dense clouds of gas and dust, surrounded by siblings in the cluster. Their orbits are often chaotic, influenced by the gravitational pull of nearby stars. Over time, these interactions can either stabilize or destabilize the quadruple configuration, offering astronomers a front-row seat to the delicate dance of celestial mechanics. What makes these young systems particularly fascinating is how they challenge existing models of star formation. For instance, astronomers have long debated whether quadruple systems form through fragmentation, a process where a single gas cloud splits into multiple stars, or through capture, where stars gravitationally bind to one another after forming separately. In star clusters where stellar densities are high, the likelihood of capture scenarios increases, but fragmentation still plays a crucial role. Observing young quadruples helps researchers weigh the importance of each process, refining our understanding of how these intricate systems come to be. Another intriguing aspect of these systems is their potential to harbor protoplanetary disks, vast, rotating disks of gas and dust that could one day form planets. In the turbulent environment of a star cluster, these disks face constant bombardment from stellar winds and radiation, making their survival a testament to the resilience of planet-forming processes. Studying these disks in quadruple systems not only sheds light on planetary formation, but also raises questions about the habitability of worlds born in such dynamic settings. Would planets orbiting these stars face an ever-changing sky, with multiple suns rising and setting in unpredictable patterns? Moreover, the study of young quadruples in star clusters provides insights into the role of external perturbations. Imagine a quadruple system peacefully orbiting within a cluster when a passing star or a nearby supernova sends shockwaves through the region. Such events can dramatically alter the system's dynamics, ejecting one or more stars or even triggering the formation of new celestial objects. These perturbations offer a glimpse into the precarious balance that governs the survival of quadruple systems in their early years. As we examine these young quadruples, we are reminded of the intricate interplay between environment and evolution in the cosmos. Each observation brings us closer to unraveling the mysteries of how these systems emerge, stabilize, and sometimes unravel. But the story doesn't end here. From the turbulent beginnings of young quadruples, we now turn our attention to the rarity of quadruple systems as a whole, a puzzle that invites us to explore why these celestial configurations are so uncommon compared to simpler binary or triple systems. The journey continues. Shifting our gaze from the bustling star clusters and their young quadruples, we now arrive at a cosmic mystery that has puzzled astronomers for decades. Why are quadruple star systems so rare? To put this into perspective, imagine a crowded ballroom filled with dancers. Pairs effortlessly find each other, and trios form with a bit of coordination. But gathering 4 dancers in perfect harmony requires much more precision, and the same is true for stars. In the universe, binary systems are the rule rather than the exception, with triple systems being less common but still fairly frequent. Quadruple systems, however, are like the elusive unicorns of the stellar world, and understanding their scarcity offers a fascinating glimpse into the mechanics of the cosmos. One reason quadruple systems are so uncommon lies in the delicate balance required for their formation. Think of stars as cosmic building blocks. In regions where stars form, gas clouds fragment under the pull of gravity, creating clumps that eventually ignite as stars. For a quadruple system to emerge, this process must produce not just 2 or 3 but 4 stars in close enough proximity to become gravitationally bound. The odds of this happening are significantly lower than for binaries or triples, simply because the conditions need to be just right, like hitting a bullseye on a moving target. If the stars form too far apart, they may never interact closely enough to establish stable orbits, while forming too close together can lead to destructive collisions or ejections. Another factor contributing to the rarity of quadruple systems is their inherent instability. Picture a group of 4 dancers again, but this time spinning in intricate patterns. Maintaining their formation requires constant adjustments to avoid collisions or someone being flung out of the group. Similarly, quadruple star systems are prone to chaotic gravitational interactions, especially during their early years. These interactions can result in 1 or more stars being ejected from the system, leaving behind a simpler binary or triple configuration. In fact, many of the binaries and triples we observe today might have started as quadruples that unraveled over time, adding another layer to the cosmic puzzle. External influences also play a role in the scarcity of quadruple systems. Consider a quadruple system nestled within a star cluster. The gravitational tug from nearby stars or even distant encounters with passing objects can disrupt the delicate balance of the system. These external forces can destabilize orbits, leading to the breakup of the quadruple arrangement. In contrast, binaries and triples are often more resilient to such perturbations, making them more likely to survive in the long run. Yet, despite their rarity, quadruple systems offer an invaluable opportunity to study the universe's most intricate gravitational choreographies. Their existence challenges astronomers to refine models of star formation and dynamical evolution, pushing the boundaries of our understanding. Why do some quadruples endure while others fall apart? What can their survival tell us about the conditions of their birth? These questions linger in the minds of researchers, hinting at deeper cosmic truths. As we marvel at the scarcity of quadruple systems, we prepare to explore how gas disks play a crucial role in their formation and stabilization, adding another piece to the puzzle of these celestial rarities. Stepping into the heart of how quadruple star systems manage to form and endure, we encounter an unsung hero of the cosmic stage, gas disks. These sprawling, spinning structures made of gas and dust might not sound glamorous, but they are essential to the birth and survival of these rare stellar quartets. Imagine a cosmic nursery where stars are born amidst swirling clouds of material. In this environment, gas disks act like a gravitational glue, helping to hold the forming stars together and guiding their movements into stable configurations. Gas disks begin their role early in the process during the collapse of a massive molecular cloud. As the cloud fragments and starts forming stars, the leftover material flattens into a spinning disk around the emerging system. This disk doesn't just feed material to the growing stars, it also exerts gravitational influences that can smooth out irregularities in their orbits. Think of it as a cosmic dance instructor, gently nudging each star into the right position and rhythm. Without this stabilizing influence, the stars might drift apart or spiral into chaotic interactions that could tear the system apart. But gas disks do more than just help quadruple systems form. They also play a critical role in keeping these systems stable over time. Picture the disk as a kind of buffer zone, absorbing excess energy from gravitational tugs and nudges between the stars. This energy dissipation helps prevent one or more stars from being flung out of the system during those early, turbulent years. In some cases, the disk can even facilitate the transfer of angular momentum, fine-tuning the orbits of the stars to create a delicate but enduring balance. Interestingly, gas disks might also influence the architecture of quadruple systems. Simulations suggest that these disks can encourage the formation of hierarchical structures, where two pairs of stars orbit each other in a larger, nested pattern. This arrangement is much more stable than a free-for-all configuration, where all four stars interact chaotically. The disk's role in sculpting these orderly systems highlights its importance not just as a passive bystander, but as an active participant in shaping the dynamics of quadruple star systems. To bring this concept closer to home, consider Saturn and its iconic rings. The rings are essentially a flattened disk of particles, and just as they influence the orbits of Saturn's moons, gas disks in star-forming regions help maintain harmony among multiple stellar bodies. This parallel provides a glimpse into the elegance of celestial mechanics, where simplicity and complexity coexist in mesmerizing ways. As we continue our journey through the mysteries of quadruple star systems, the next discovery brings us to an intriguing phenomenon: how these systems can act as magnifying lenses for distant objects, opening a new window into the universe's farthest reaches. Now, let's shift our gaze to a truly fascinating phenomenon where quadruple star systems become cosmic magnifying glasses, revealing secrets from the farthest corners of the universe. This discovery revolves around the concept of microlensing, a process that occurs when the gravity of a massive object, like a star system, bends and amplifies the light from an object located far behind it. In the case of quadruple star systems, their unique gravitational fields can turn them into powerful natural lenses, offering astronomers an extraordinary tool to study objects that would otherwise remain invisible. To understand how this works, imagine standing on a beach and looking at the waves bending around a rock. The rock changes the path of the water, creating a pattern that wouldn't exist without it. Similarly, the gravity of a quadruple star system warps the fabric of space-time, altering the path of light from a distant star or galaxy. This bending of light causes the distant object to appear brighter for a brief period, allowing scientists to detect and analyze it. What makes quadruple systems particularly special is their complex gravitational interactions. With four stars contributing to the lensing effect, the resulting magnification can be more intricate and revealing compared to simpler systems. One remarkable example of this phenomenon involves systems where the stars are not evenly spaced but instead form a dynamic, hierarchical structure. In these cases, the varying gravitational pulls from each pair of stars create a kind of ripple effect, producing unique microlensing patterns. These patterns can provide valuable insights into the distribution of mass within the quadruple system itself, as well as the properties of the distant object being magnified. It's like piecing together a cosmic puzzle where the lensed light serves as clues to unlock the mysteries of both the foreground and background objects. Quadruple star systems acting as microlenses have already helped astronomers identify exoplanets, distant stars, and even faint galaxies that lie billions of light-years away. For instance, in one notable observation, a quadruple system amplified the light from a dim star in the Milky Way's halo, revealing details about its composition and motion. This discovery underscores how these stellar quartets can serve as unintentional telescopes, expanding our ability to explore the universe. It's a humbling reminder of how interconnected celestial objects are, even across vast distances. As we marvel at this incredible application of quadruple star systems, it's worth considering the broader implications of microlensing. This natural phenomenon not only enhances our understanding of distant objects, but also offers a glimpse into the unseen architecture of the cosmos. With that in mind, our journey continues to another captivating aspect, the puzzle of orbital inclinations, where we'll uncover how the tilt and orientation of orbits can shed light on the origins of these remarkable systems. Now that we've explored how quadruple star systems can act as natural telescopes, let's turn our attention to another intriguing mystery, the puzzle of orbital inclinations. This aspect of quadruple systems holds critical clues about their formation and evolution, offering a glimpse into the conditions that shaped these stellar quartets. Orbital inclination refers to the tilt of a star's orbit relative to a reference plane, and in quadruple systems, understanding these tilts can reveal a great deal about their history. In simpler terms, imagine spinning a hula hoop on different angles while holding it in front of you. Sometimes it's tilted sideways, sometimes upright, and other times somewhere in between. Each tilt represents a different orbital inclination. In quadruple star systems, these inclinations are rarely random. They follow patterns that hint at the gravitational dance these stars have performed over millions or even billions of years. By studying these patterns, astronomers can trace the steps of this cosmic ballet and uncover how these systems came to be. What makes this particularly fascinating is the diversity of configurations we observe. Some quadruple systems have orbits that are nearly aligned, suggesting they formed from a single rotating disk of gas and dust. Others exhibit wildly differing inclinations, indicating a more chaotic origin, possibly involving close encounters with other stars or even the capture of one star by a pre-existing triple system. These differences tell us that nature has more than one way of assembling these complex systems, and each method leaves its own signature in the orbital inclinations. One compelling example comes from simulations that model the early lives of quadruple systems. These simulations show that when stars are born together in a dense stellar nursery, their orbital inclinations tend to align because they inherit the same angular momentum from the parent cloud. However, if a passing star exerts a gravitational tug or if two binary systems merge, the inclinations can become misaligned, creating the chaotic arrangements we sometimes observe. This interplay of forces highlights the delicate balance between order and chaos in the universe. Understanding these inclinations isn't just about piecing together the past, it also helps us predict the future. For instance, systems with highly misaligned orbits may be more prone to ejecting one of their members, creating rogue stars that drift through space alone. By contrast, systems with aligned orbits are often more stable, capable of maintaining their intricate configurations for billions of years. These predictions give astronomers a way to test theoretical models against real-world observations, refining our understanding of stellar dynamics. As we dig deeper into the puzzle of orbital inclinations, we're reminded of how much these systems can teach us about the universe's grand design, but the intrigue doesn't stop here. Moving forward, we'll examine how gas disks play a crucial role in the formation and stabilization of quadruple systems, adding another layer to this cosmic story. With the intricate role of gas disks freshly in mind, let's shift our focus to another captivating aspect of quadruple star systems, those that host white dwarfs. These stellar remnants, the collapsed cores of stars that have exhausted their nuclear fuel, might seem like quiet relics of the cosmos, but in quadruple systems, they often play a pivotal role in some of the universe's most explosive events. White dwarfs are fascinating because they represent the final stage of life for stars like our Sun. But when they're part of a quadruple system, their story becomes even more complex. In these systems, white dwarfs can interact with their companion stars in ways that make them potential supernova progenitors. A supernova is one of the brightest events in the universe, and understanding how they form is like piecing together the ultimate cosmic puzzle. Take, for example, a scenario where a white dwarf orbits closely with another star within the quadruple system. If the white dwarf pulls material like hydrogen or helium from its companion, it can gradually build up mass. But this growth isn't limitless. When the white dwarf reaches a critical mass known as the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can trigger a thermonuclear explosion, creating what's known as a Type Ia supernova. These explosions are so bright that they can outshine entire galaxies for a short time, and are crucial tools for measuring cosmic distances. What makes quadruple systems particularly intriguing in this context is the added complexity of their gravitational interactions. In a simpler binary system, the process leading to a supernova might be relatively straightforward. But in quadruple systems, the presence of multiple stars introduces a dynamic interplay of forces that can accelerate or disrupt the buildup of material on the white dwarf. For example, a distant binary pair within the quadruple system could exert gravitational tugs that alter the orbits of the inner stars, changing how material flows between them. These kinds of interactions mean that quadruple systems could produce supernova in ways that simpler systems cannot, offering unique insights into the conditions that lead to these dramatic events. Interestingly, not all white dwarfs in quadruple systems are destined to explode. Some might instead form stable configurations, quietly orbiting alongside their companions for billions of years. Astronomers study these systems to learn which conditions favor supernova formation and which do not. By doing so, they can refine models of stellar evolution and better predict the outcomes of these complex systems. Beyond their role in supernova, these white dwarfs also serve as cosmic time capsules. Their compositions and temperatures can reveal details about the stars they once were and the environments in which they formed. In quadruple systems, where multiple stars influence one another over time, the histories preserved in these white dwarfs become even richer and more intricate. As we marvel at the explosive potential of white dwarfs in quadruple systems, it's worth noting that these remnants are not just harbingers of destruction, they're also keys to unlocking deeper knowledge about the universe. But the story doesn't end here. Moving forward, we'll explore an even more enigmatic question: whether dark matter might play a role in shaping the dynamics of these stellar quartets. As we venture further into the cosmic unknown, let's turn our attention to a mystery that has puzzled scientists for decades: dark matter. This invisible substance, which makes up about 85% of the universe's mass, doesn't emit, absorb, or reflect light, making it nearly impossible to detect directly. Yet its gravitational effects are undeniable, shaping galaxies, clusters, and even the largest structures in the universe. But could dark matter also influence something as intricate as a quadruple star system? It's a question that pushes the boundaries of our understanding and invites us to imagine the universe in a whole new way. Dark matter is often thought of on grand scales, like galaxies or galaxy clusters, But when we zoom into smaller systems like quadruple stars, its potential role becomes both fascinating and complex. In these systems, the gravitational pull between the stars governs their movements, creating delicate orbital dances. But what if there's an additional, unseen force at play? Dark matter, though diffuse, might exert subtle gravitational influences that nudge the stars in ways we don't yet fully grasp. For instance, in regions of space where dark matter is more concentrated, its presence could slightly alter the orbital dynamics of quadruple systems, introducing unpredictability or even stabilizing certain configurations. Consider this: if dark matter is unevenly distributed in the vicinity of a quadruple system, it could create pockets of higher density that act like invisible barriers or attractors, subtly shaping the paths of the stars. Over millions or billions of years, these tiny gravitational tugs might accumulate, leading to observable effects on the system's stability or evolution. While astronomers are still far from proving such interactions, the possibility itself opens up exciting new avenues for research. By studying quadruple systems in different parts of the galaxy, scientists hope to uncover patterns or anomalies that could hint at the influence of dark matter. Of course, this is all speculative at this stage. Detecting dark matter's effects on such a small scale is incredibly challenging, given that its presence is usually inferred from much larger cosmic structures. But the beauty of science lies in asking bold questions and testing the limits of what we know. By exploring how dark matter might affect quadruple star systems, we're not just learning about these stellar quartets, we're also deepening our understanding of dark matter itself. Could these systems serve as natural laboratories for studying this enigmatic substance? Only time and further research will tell. As we ponder the unseen forces that might shape the dance of quadruple stars, let's now shift our focus to another intriguing aspect of these systems: their long-term stability. Using advanced computer simulations, scientists are beginning to predict how these complex arrangements might endure or unravel over billions of years, offering a glimpse into the future of these cosmic marvels. Moving from the mysteries of dark matter, let's now explore how scientists are using cutting-edge technology to peer into the future of quadruple star systems. Through advanced computer simulations, researchers are unraveling the intricate dynamics that determine whether these stellar quartets will remain stable or eventually fall apart. These simulations are like a crystal ball for astronomers, offering predictions that span billions of years and shedding light on the delicate balance that keeps these systems intact. To understand the long-term stability of quadruple star systems, scientists first input vast amounts of data into their models. This includes the masses of the stars, their distances from one another, and the specific shapes and orientations of their orbits. By factoring in these variables, the simulations can recreate the gravitational interactions that govern the system. What makes these models truly remarkable is their ability to account for even the smallest perturbations, tiny shifts in motion that might seem insignificant at first but could grow over time to dramatically alter the system's fate. One fascinating outcome of these simulations is the discovery of tipping points. These are moments when a seemingly stable quadruple system can suddenly become chaotic. For example, if one star in the system loses too much mass, perhaps through stellar winds or by transferring material to a companion, the delicate balance of gravitational forces can be disrupted. This might cause one or more stars to be ejected from the system entirely, leaving behind a simpler binary or even a lone star. Such ejections are not just theoretical. Astronomers have observed their aftermath in the form of runaway stars speeding through the galaxy. But stability isn't always about avoiding chaos. In some cases, quadruple systems can find a kind of equilibrium, even in the face of complex gravitational interactions. The simulations reveal that certain orbital configurations are more resilient than others. For instance, systems with a clear hierarchy, where two close binary pairs orbit each other at a much greater distance, are more likely to endure over time. This hierarchical structure minimizes close encounters between the stars, reducing the chances of disruptive gravitational tugs. What's particularly intriguing is how these simulations allow scientists to test different scenarios. By tweaking variables such as the initial positions of the stars or the presence of external forces like passing stars or galactic tides, researchers can explore how sensitive these systems are to changes. Some simulations even incorporate the effects of dark matter, continuing the thread of our earlier discussion. While dark matter's influence is subtle, these models show that it could contribute to the long-term evolution of quadruple systems, either by stabilizing them or by nudging them toward instability. The results of these simulations aren't just theoretical exercises, they have practical implications for understanding the universe. For example, by identifying which systems are likely to remain stable, astronomers can focus their observations on quadruple systems that might host planets or other interesting phenomena. Stability is a key factor in determining whether planets could form and survive in such environments, making these simulations an essential tool for exoplanet research. As we marvel at the power of these computer models to predict the future of quadruple star systems, it's worth noting that they also remind us of the universe's unpredictability. No matter how precise the simulations, there will always be variables we can't fully account for, whether it's the influence of dark matter or the effects of unseen companions lurking just beyond our detection. Yet, it's this blend of precision and mystery that makes the study of quadruple systems so captivating. With these insights into the long-term stability of quadruple star systems, we now turn our attention to the dynamic interactions between their binary pairs. These interactions are not just about gravitational forces, they're also about energy exchange, a process that can shape the system's evolution in surprising ways. Shifting our focus now, let's dive into the fascinating dance of binary-binary interactions within quadruple star systems. These systems are not just a collection of stars orbiting in isolation, they are dynamic environments where energy exchange plays a pivotal role in shaping their evolution. Imagine two pairs of stars, each locked in their own binary embrace, yet also orbiting a common center of mass. This intricate choreography is where the magic happens, as energy flows back and forth between the pairs, influencing their orbits and even their long-term survival. At the heart of these interactions is the concept of energy transfer. When two binary pairs are close enough, their gravitational pulls can cause shifts in momentum and energy. For example, if one binary pair has a tighter, faster orbit, it can temporarily lend some of its kinetic energy to the other pair during a close pass. This exchange can alter the shape and orientation of their orbits, sometimes stabilizing the system and other times pushing it toward chaos. It's a delicate balance where even small changes can have cascading effects over time. One remarkable outcome of these energy exchanges is the potential for orbital resonance. This occurs when the orbital periods of the two binary pairs fall into a simple ratio, like 2:1 or 3:2. When this happens, their gravitational tugs reinforce each other at regular intervals, creating a synchronized rhythm that can either stabilize the system or amplify its instability. Think of it like pushing a swing. If you time your pushes just right, the swing goes higher and higher. But if you're offbeat, the motion becomes erratic and unpredictable. Scientists have also observed that these interactions can lead to dramatic transformations within quadruple systems. In some cases, energy exchange causes one binary pair to tighten its orbit while the other pair drifts farther apart. This process, known as Kozai-Lidov cycling, can even trigger events like stellar mergers or the ejection of a star. It's a reminder that these systems are far from static. They are constantly evolving, driven by the push and pull of their gravitational bonds. What's especially intriguing is how these interactions can shed light on the history of quadruple systems. By studying the current orbits and energy states of the stars, researchers can work backward to reconstruct past events. For instance, they might discover evidence of a close encounter that temporarily disrupted the system or a period of stability that allowed planets to form. These clues help piece together the cosmic puzzle of how quadruple systems form and endure over billions of years. As we continue exploring the mysteries of quadruple star systems, these binary interactions highlight the complexity and beauty of their dynamics. They remind us that even in the vastness of space, the smallest exchanges of energy can shape the fates of entire stellar families. And speaking of shaping fates, our next discovery takes us into the realm of the extraordinary. Could quadruple systems harbor not just stars but also black holes? Let's find out. Now, let's take a bold leap into the realm of the truly extraordinary quadruple black hole systems. While the idea might sound like the stuff of science fiction, it's a tantalizing possibility that astronomers are actively exploring. Imagine not just one, but 4 black holes locked in a gravitational ballet, each warping space-time in ways that challenge our understanding of the universe. This isn't just theoretical speculation. The hunt for such systems is driven by the tantalizing clues we've already uncovered in the cosmos. To understand why quadruple black hole systems are so fascinating, we first need to grasp how black holes form in the first place. When massive stars collapse at the end of their lifespans, they can leave behind these enigmatic remnants, regions of space where gravity is so strong that not even light can escape. In some cases, these black holes are solitary, wandering the galaxy alone. But in denser environments like star clusters, they can become part of multi-star systems. If a quadruple star system undergoes a series of dramatic events, such as supernova explosions or gravitational interactions, it's conceivable that all 4 stars could eventually collapse into black holes, creating a quadruple black hole system. The big question, of course, is whether we could ever detect such a system. Black holes themselves are invisible, but we can observe their effects on nearby matter and light. For instance, when black holes orbit each other, they create ripples in spacetime known as gravitational waves. These waves, first predicted by Einstein's theory of general relativity, are now being detected by observatories like LIGO and Virgo. While most detections so far have involved pairs of black holes, the possibility of detecting a quadruple system's unique gravitational wave signature is an exciting frontier. The signal would be incredibly complex, with overlapping waves from multiple sources, offering a treasure trove of data for scientists to analyze. Another way to spot a quadruple black hole system could be through its interaction with surrounding stars or gas. If the black holes are actively pulling in material, they might emit powerful jets of radiation, creating what's known as an active galactic nucleus. These bright beacons could provide indirect evidence of the system's existence. Additionally, if the black holes pass in front of a distant star or galaxy, their gravity could bend and magnify the light, a phenomenon known as gravitational lensing. This effect could serve as another clue in the search for these elusive systems. What makes the quest for quadruple black holes so compelling is the potential insights they offer into the universe's most extreme environments. Studying such systems could help us better understand how black holes form, how they interact with each other, and even how galaxies evolve over time. They might also provide a unique testing ground for theories of gravity and the behavior of spacetime under extreme conditions. And while we haven't found a confirmed quadruple black hole system yet, the search itself is pushing the boundaries of our technology and imagination. As astronomers continue combing the cosmos for these hidden giants, one thing is certain: the discovery of a quadruple black hole system would be a monumental breakthrough. It would not only rewrite our understanding of black holes, but also offer a glimpse into the most intricate and powerful forces shaping the universe. And speaking of powerful forces, our next discovery delves into the intricate details of quadruple systems catalogued in multiple star catalogs, celebrating the diversity and complexity of these stellar families. Shifting our gaze from the tantalizing mystery of quadruple black holes, let's now turn our attention to something a little more grounded but no less extraordinary: the fascinating records found in multiple star catalogs. These catalogs serve as cosmic archives, meticulously documenting the diverse range of quadruple star systems scattered across the universe. They not only help us appreciate the sheer variety of these stellar families, but also deepen our understanding of their unique behaviors and configurations. One of the most intriguing entries in these catalogs is the system known as Castor, located in the constellation Gemini. Castor is a celebrated example of a hierarchical quadruple system, where two pairs of stars orbit a common center of mass. What makes Castor particularly special is that its components are not identical twins but rather a mixed bag of stellar types, including hot, bright stars as well as cooler, dimmer ones. This diversity showcases how quadruple systems can host stars at different stages of their life cycles, offering astronomers a natural laboratory to study stellar evolution. Another remarkable catalogued system is KIC 48622625. While its name might sound like a jumble of numbers, this system has earned its place in the spotlight due to its circumbinary planet, a world that orbits two of the stars in the system. This discovery highlights how quadruple systems can challenge our assumptions about planetary formation and stability, proving that even in the most complex environments, nature finds a way to create and sustain worlds. Then there's the curious case of HD 98800, a quadruple system that stands out for its protoplanetary disk. This disk, made of gas and dust, encircles one of the binary pairs within the system, offering a glimpse into the early stages of planet formation. HD 98800 reminds us that the universe is still hard at work crafting new celestial bodies, even within the intricate dynamics of multi-star systems. These catalogs also reveal how quadruple systems differ not just in their structure but in their ages, compositions, and environments. Some systems are relatively young, residing in star-forming regions, while others are ancient, their stars having aged gracefully over billions of years. By studying this diversity, astronomers gain a broader perspective on how quadruple systems fit into the grand tapestry of the cosmos, influencing everything from star formation to the evolution of galaxies. As we celebrate these catalogued wonders, it becomes clear that quadruple star systems are anything but monolithic. They are as varied and vibrant as the stars themselves, each one telling its own unique story. And speaking of stories, our next discovery zooms out even further, examining how these intricate stellar families contribute to the dynamic dance of entire galaxies. As we venture beyond the individual tales of quadruple star systems, let's now explore how these intricate stellar families play a role in the grand cosmic ballet of galaxies. Though they may seem small in the vastness of space, quadruple systems have a surprising influence on the environments they inhabit, contributing to the dynamic processes that shape galaxies over millions and billions of years. Quadruple star systems, with their complex gravitational interactions, can act as tiny but powerful engines within galaxies. Their movements, though minuscule on a galactic scale, add up when you consider the sheer number of such systems scattered throughout a galaxy. These systems can influence the motion of surrounding stars and gas clouds, stirring up the galaxy's structure in subtle yet meaningful ways. For instance, when quadruple systems eject one of their members due to unstable orbits, the runaway star can travel at incredibly high speeds, carving paths through interstellar material and triggering waves of star formation in its wake. But the impact doesn't stop there. Quadruple systems also contribute to the distribution of elements across galaxies. As stars within these systems evolve, they fuse lighter elements into heavier ones, eventually dispersing these materials through stellar winds or even explosive events like supernova. This enrichment of the galaxy's chemical makeup is crucial for the birth of new stars and planets, ensuring a continuous cycle of creation and renewal. Interestingly, quadruple systems may also play a role in the stability or instability of galaxies. The gravitational tugs and pulls within these systems can sometimes resonate with larger structures like galactic arms, amplifying or dampening their motion. Scientists speculate that even small perturbations caused by quadruple systems could ripple outward, affecting the galaxy's overall shape and behavior over time. What's truly fascinating is how these systems serve as microcosms of the larger universe. Just as quadruple stars orbit each other in a delicate balance, galaxies themselves are part of an even grander system, interacting and evolving through similar gravitational principles. By studying quadruple systems, astronomers gain insights into the fundamental forces that govern not just individual stars but entire galaxies. With that broader perspective in mind, we now turn our attention to a more elusive aspect of these systems, those quadruples that remain hidden from view, shrouded in mystery due to the limitations of our current observational tools. These unresolved quadruples challenge astronomers to think creatively and push the boundaries of how we study the universe. Now, let's shine a light on a particularly intriguing challenge that astronomers face when studying quadruple star systems, those elusive systems that remain unresolved, their true nature concealed from even the most advanced telescopes. These unresolved quadruples pose a fascinating mystery as they blend into the cosmos like hidden gems, their dual binary dance remaining just out of sight. Unresolved quadruples are systems where the individual stars are so close together or so far away from Earth that they appear as a single point of light even through powerful instruments. This optical illusion creates a puzzle for researchers who must rely on indirect methods to tease apart their true structure. Imagine trying to distinguish individual voices in a choir when all you hear is a unified melody. It's not impossible, but it requires skill, patience, and the right tools. Similarly, astronomers employ techniques like spectroscopy, astrometry, and photometric variability studies to uncover the hidden identities of these stellar quartets. One of the key methods used to identify unresolved quadruples is analyzing subtle shifts in light patterns. For instance, stars in such systems often display complex brightness variations caused by eclipses, stellar activity, or gravitational interactions. By carefully studying these fluctuations, scientists can infer the presence of multiple stars and even map out their orbital dynamics. It's like piecing together a jigsaw puzzle without knowing what the final picture looks like. Every tiny clue brings the bigger picture into sharper focus. Another approach involves high-resolution imaging techniques such as interferometry, which combines the power of multiple telescopes to simulate a much larger instrument. This technological marvel allows astronomers to peer deeper into the heart of these systems, sometimes revealing previously unknown components. However, even with these advancements, some quadruples remain stubbornly enigmatic, their secrets locked away by the sheer vastness of space or the limitations of current technology. The challenge of unresolved quadruples isn't just about identifying them, it's also about understanding their role in the larger fabric of the universe. These hidden systems may harbor clues about star formation, gravitational interactions, and the evolution of galaxies. Every unanswered question about an unresolved quadruple is a doorway to deeper exploration, pushing scientists to innovate and refine their methods. As we continue this cosmic journey, let's now shift our gaze to how quadruple star systems have captured the imagination of storytellers and creators, appearing in science fiction as settings for adventure, drama, and mystery, a testament to their enduring allure. Stepping into the realm of imagination, we find that quadruple star systems have not only intrigued scientists, but have also sparked boundless creativity among writers and filmmakers. These complex celestial arrangements often serve as the perfect backdrop for tales of adventure, mystery, and even existential exploration. Science fiction has long been fascinated by the idea of multiple suns in the sky, and quadruple systems take this concept to breathtaking extremes. Picture a world where four stars rise and set in an ever-changing dance, their light painting the horizon in hues no earthly sky could replicate. Such settings allow creators to craft stories that push the boundaries of human experience, offering a glimpse into lives shaped by cosmic chaos and wonder. In literature, quadruple star systems frequently appear as the homes of advanced alien civilizations, or as the sites of uncharted planetary systems brimming with secrets. For instance, some novels explore the psychological and societal effects of living under multiple suns. Would the constant shifts in daylight influence the rhythm of life, or even the development of culture and philosophy? Other stories delve into the challenges of survival on planets orbiting such systems, where gravitational forces and fluctuating climates create harsh and unpredictable environments. These narratives often highlight humanity's resilience and curiosity, reminding us of our enduring desire to understand and adapt to the unknown. Film and television have also embraced the visual spectacle of quadruple systems, using them to evoke awe and wonder. Imagine a climactic scene where characters stand on a planet bathed in the golden glow of two suns while two others hover faintly on the horizon, their light refracting through an alien atmosphere. These visuals not only captivate audiences but also serve as metaphors for the complexity and beauty of the universe. Even in science fiction games, quadruple systems often feature as the settings for epic quests, where players navigate intricate star maps and uncover hidden worlds, blending scientific inspiration with boundless creativity. What makes these portrayals so compelling is how they reflect our own fascination with the cosmos. While science fiction takes creative liberties, it often draws from real astronomical phenomena, planting seeds of curiosity about the actual science behind these systems. By weaving quadruple stars into their stories, creators invite us to dream of possibilities far beyond our own solar system, while also encouraging us to look up and wonder what else might be out there. As we move forward, let's turn our attention to how stellar winds from these systems interact, shaping their surroundings in ways that are both dramatic and scientifically significant. As we shift our gaze to the dynamic forces at play, we encounter a fascinating phenomenon that shapes the environments of quadruple star systems, stellar winds. These powerful streams of charged particles ejected by stars in every direction hold the key to understanding how these systems interact with their surroundings. When multiple stars are involved, their winds don't just drift off into space, they collide, mingle, and create cosmic structures that are as intricate as they are breathtaking. In a quadruple system, each star contributes its own stellar wind, and the combined effect can be likened to a celestial symphony. Imagine four musicians playing different instruments. Each wind carries its own energy, speed, and density, depending on the size and activity of the star. When these winds meet, they can either reinforce one another or clash dramatically. For instance, if one star is much larger and hotter than its companions, its wind might dominate the system, carving out vast cavities in the surrounding space and pushing material far into the interstellar medium. These interactions can form shock waves which heat up the gas to millions of degrees, making the region glow brightly in X-rays. But the story doesn't end there. The interplay of stellar winds also influences any planets or dust disks within the system. Think of it as a cosmic weather system, where the winds shape the environment much like Earth's winds sculpt sand dunes or erode mountains. In quadruple systems, this space weather can strip atmospheres from planets, redistribute material in protoplanetary disks, or even trigger the formation of new celestial objects by compressing gas clouds. Scientists study these effects to better understand how such chaotic environments might still allow for the birth and survival of planets despite the turbulent conditions. What's particularly intriguing is how these stellar winds can reveal hidden aspects of the system. When winds collide, they produce observable signatures such as glowing nebulae or high-energy radiation. These signatures act like fingerprints, allowing astronomers to map the dynamics of the system and piece together its history. For example, by analyzing the intensity and direction of these emissions, researchers can infer the relative positions and velocities of the stars, painting a clearer picture of their orbital dance. As we marvel at the sheer complexity of these interactions, we're reminded of the delicate balance that governs quadruple star systems. Each star exerts its influence, yet the whole system remains interconnected, shaped by forces that are both destructive and creative. And with that understanding, we set the stage for our next discovery, where we'll uncover how these intricate orbital dances can sometimes lead to surprising and even chaotic outcomes. Moving from the intricate ballet of stellar winds, we now turn our attention to another captivating feature of quadruple star systems: variable stars. These celestial performers are anything but static, as their brightness fluctuates over time, creating a natural light show that has intrigued astronomers for centuries. In quadruple systems, the presence of variable stars adds an extra layer of complexity and wonder, offering a unique window into the inner workings of stars themselves. Variable stars come in many types, but they all share one thing in common: their luminosity changes due to physical processes occurring within or around them. In a quadruple system, these fluctuations can be influenced by the gravitational tugs of companion stars, making their behavior even more dynamic and unpredictable. For instance, some variable stars pulsate, expanding and contracting like cosmic lungs. Others are eclipsed by their companions, causing periodic dips in brightness that can be observed from Earth. By studying these changes, scientists can uncover vital clues about the star's sizes, temperatures, and internal structures. What makes variable stars in quadruple systems particularly fascinating is the interplay between their natural variability and the gravitational forces of their neighboring stars. Imagine a star whose brightness waxes and wanes due to pulsations, but whose rhythm is occasionally disrupted by the gravitational pull of a nearby companion. This interaction can produce complex patterns of variability that challenge our understanding of stellar physics. In some cases, these patterns can even reveal hidden companions that might otherwise go undetected, as their influence becomes apparent through subtle changes in the variable star's behavior. Moreover, quadruple systems with variable stars serve as natural laboratories for testing theories of stellar evolution. By observing how these stars change over time, astronomers can refine models that predict how stars age and interact within multi-star environments. For example, if one star in the system is a Cepheids variable, a type of star whose pulsations are closely linked to its intrinsic brightness, scientists can use it as a cosmic yardstick to measure vast distances across the universe. When such a star resides in a quadruple system, its variability becomes an even more powerful tool, as the gravitational dynamics of the system provide additional data points for analysis. But the intrigue doesn't stop there. Variable stars in quadruple systems also offer insights into the role of mass transfer and tidal forces. When a variable star orbits close to its companions, material can be pulled from its outer layers, creating streams of gas that glow brightly as they heat up. These interactions can lead to spectacular displays, such as accretion disks around compact objects or sudden outbursts of light known as nova. Each of these phenomena tells a story about the delicate balance between stability and chaos within the system. As we explore these shimmering beacons of variability, we're reminded of the intricate connection between individual stars and the systems they inhabit. The dance of light and gravity within quadruple systems not only highlights the beauty of the cosmos, but also deepens our understanding of the forces that shape it. And with that, we prepare to venture into another captivating discovery, one that delves into the enigmatic process of compact object formation within these stellar quartets. Shifting our gaze from the dazzling variability of stars, we now delve into one of the most profound mysteries of quadruple star systems, the formation of compact objects. These dense remnants, such as neutron stars and black holes, are the final acts in the life cycles of massive stars, and their presence within quadruple systems adds another layer of intrigue to these already complex cosmic arrangements. In quadruple systems, the formation of compact objects becomes a particularly fascinating process. When a massive star exhausts its nuclear fuel, it can no longer counteract the inward pull of gravity, leading to a catastrophic collapse. This collapse can result in the birth of a neutron star, an incredibly dense object where a mere teaspoon of material would weigh billions of tons on Earth, or a black hole, a region of space where gravity is so strong that not even light can escape. But what makes this process especially captivating in quadruple systems is the influence of neighboring stars. Imagine a massive star nearing the end of its life, surrounded by three companions locked in a gravitational dance. The proximity of these companions can dramatically alter the star's fate. For instance, if one of the companion stars strips material from the dying star, a process known as mass transfer, it can either hasten or delay the star's collapse. This interaction can lead to the formation of exotic objects like millisecond pulsars, which are neutron stars spinning at incredibly rapid rates due to the accretion of material from a companion. These systems essentially become natural laboratories for studying the extreme physics of stellar remnants, but the story doesn't end with formation. Once a compact object emerges within a quadruple system, its gravitational presence can profoundly reshape the dynamics of the entire system. For example, the intense gravitational pull of a neutron star or black hole can cause dramatic disruptions in the orbits of its companions. In some cases, this might even lead to the ejection of one or more stars from the system, leaving behind a smaller but more tightly bound configuration. These ejected stars, hurtling through space at tremendous velocities, are sometimes referred to as runaway stars, and their origins are often traced back to such violent events. Another remarkable phenomenon is the potential for quadruple systems to host multiple compact objects. Picture two neutron stars orbiting each other within the larger quadruple system, their mutual gravitational attraction causing them to spiral closer over time. As they do, they emit gravitational waves, ripples in the fabric of spacetime predicted by Einstein's theory of general relativity. These waves carry away energy, causing the stars to inch ever closer until they eventually collide in a cataclysmic event known as a kilonova. Such collisions are not only spectacular but also crucial for the creation of heavy elements like gold and platinum, which are scattered into the cosmos. What makes quadruple systems so valuable for studying compact objects is the wealth of data they provide. The gravitational interactions within these systems allow astronomers to measure the masses, spins, and orbital parameters of neutron stars and black holes with remarkable precision. These measurements, in turn, help refine our understanding of fundamental physics, such as the equation of state for neutron star matter, a long-standing puzzle in astrophysics. Each new observation brings us closer to unraveling the secrets of these enigmatic objects. As we continue to explore the role of compact objects in quadruple systems, we are reminded of the interconnectedness of cosmic phenomena. The death of one star can shape the destiny of its companions, creating a legacy that echoes across the universe. And with that thought, we turn our attention to another intriguing aspect of these stellar quartets: the possibility of these systems serving as beacons for the search for intelligent life. As we shift our focus from the explosive remnants of stellar evolution, let's turn our gaze toward a question that has fascinated humanity for centuries: the possibility of intelligent life beyond Earth. Quadruple star systems, with their intricate gravitational dances and dynamic environments, offer a unique context for exploring this age-old mystery. Could these complex systems harbor the conditions necessary for life, or even civilizations advanced enough to communicate across the cosmos? The search for extraterrestrial intelligence, or SETI, focuses on detecting signals from intelligent civilizations, such as radio waves or laser pulses, that might indicate the presence of technological activity. While most SETI efforts have traditionally targeted single stars or binary systems, quadruple systems present an intriguing new frontier. These systems, with their multiple sources of light and energy, could theoretically provide diverse habitats for life. For example, planets orbiting within the habitable zones of one or more stars in the system might benefit from stable climates and abundant energy, essential ingredients for the emergence of complex organisms. But it's not just the potential for habitable planets that makes quadruple systems interesting for SETI. The presence of multiple massive stars, neutron stars, or even black holes within these systems could serve as natural amplifiers for signals. Imagine a civilization harnessing the gravitational pull of a neutron star to focus and direct powerful transmissions across interstellar distances. Such a scenario might sound like science fiction, but it's grounded in the same physics that allows us to study gravitational waves and other cosmic phenomena. Another compelling idea is the possibility of advanced civilizations using quadruple systems as navigational beacons. The unique orbital configurations and periodic eclipses within these systems could create a kind of celestial clock visible from vast distances. By encoding information into the timing or intensity of these signals, an intelligent species might create a cosmic lighthouse, drawing the attention of other civilizations. This concept ties into ongoing SETI efforts to identify patterns or anomalies in stellar behavior that could indicate deliberate communication. Of course, the challenges of life emerging in such a complex environment cannot be ignored. The gravitational chaos within quadruple systems might make stable planetary orbits rare, raising questions about whether life could ever gain a foothold. Yet, as we've seen throughout our exploration, these systems are full of surprises, defying our expectations at every turn. Perhaps life, in its infinite adaptability, could find a way to thrive even in such an unpredictable setting. As we ponder these possibilities, it's worth noting that SETI is not just about finding answers, it's about asking the right questions. Could quadruple systems be home to intelligent life? Or might they serve as stepping stones for civilizations seeking to explore the galaxy? These questions remind us of the vastness of the universe and the limits of our current understanding. And with that, we transition to the next mystery: systems exhibiting precessing orbits, where the intricate gravitational ballet of stars reveals even more about the dynamics of these cosmic wonders. What happens when the cosmic dance of stars takes an even more complex turn? In the case of quadruple star systems with precessing orbits, we find ourselves peering into a celestial ballet where the stars themselves seem to wobble and shift over time. Precession, a slow and gradual change in the orientation of orbital planes, adds yet another layer of mystery to these already intricate systems. Imagine a spinning top that wobbles as it slows down. This is akin to what occurs in certain quadruple systems, where gravitational interactions cause their orbits to shift in subtle but measurable ways. Precessing orbits occur because of the gravitational tug of war between the stars in a system. Each star exerts its own pull, and when combined with the effects of mass distribution and angular momentum, these forces can cause the orbital planes to tilt or rotate over long periods. In some cases, this precession happens over thousands or even millions of years, making it a challenge for astronomers to observe directly. Yet, thanks to advancements in technology and long-term observational studies, we're beginning to piece together the story of these gravitational interactions. For example, systems like TSE 17,290,988 have provided valuable data on how the orbital planes of stars can shift due to their mutual influences. Why does this matter? Precessing orbits not only reveal the delicate balance of forces within quadruple systems, but also offer clues about their formation and evolution. Over time, the wobbling of orbits can either stabilize or destabilize a system. In some cases, the precession can lead to dramatic outcomes, such as stars being ejected from the system or colliding with one another. These effects are particularly fascinating because they highlight the chaotic yet predictable nature of gravitational dynamics. It's a reminder that even in the vastness of space, the smallest gravitational nudges can have profound consequences. Understanding precessing orbits also deepens our appreciation for the precision of celestial mechanics. For instance, astronomers can use these systems as natural laboratories to test theories of gravity. By comparing observed precession rates with predictions from Einstein's theory of general relativity, scientists can verify the accuracy of our current models. This interplay between observation and theory showcases the beauty of astronomy, where the universe itself becomes the ultimate experiment. And as we study these systems, we gain insights not only into quadruple stars but also into the fundamental forces that govern the cosmos. With precessing orbits unraveling more of their secrets, we're reminded just how much there is to learn about the intricate relationships between stars. These gravitational dances, hidden in plain sight, challenge us to rethink our assumptions about stability and chaos in the universe. And as we marvel at these cosmic wonders, we now turn our attention to the final discovery, a forward-looking discussion on how future telescopes and technologies will unveil even more mysteries about quadruple star systems. What will these advancements reveal, and how will they reshape our understanding of the stars? Let's find out together. As we stand on the brink of a new era in astronomy, the tools of tomorrow promise to unlock even deeper secrets about quadruple star systems. Future telescopes and technologies are set to revolutionize our understanding of these celestial marvels, bringing us closer to answering questions that have lingered for decades. Imagine peering into the cosmos with instruments so advanced that they can detect the faintest flickers of light from stars located thousands of light years away. These are not scenes from a science fiction novel, but glimpses of what lies ahead thanks to innovations like the James Webb Space Telescope and the Extremely Large Telescope. These next-generation observatories will allow astronomers to study quadruple systems in unprecedented detail, capturing data that was once beyond reach. One of the most exciting advancements is the use of adaptive optics, a technology that corrects the blurring effects of Earth's atmosphere in real time. This means we'll no longer be limited by the distortions that have historically hindered ground-based observations. With sharper images and more precise measurements, scientists will be able to map the intricate orbital dynamics of quadruple systems with greater accuracy than ever before. Additionally, space-based interferometers will push the boundaries of resolution, enabling researchers to study the faint signals of eclipsing binaries or circumbinary planets within these complex systems. These tools will not only help us confirm existing theories, but also uncover entirely new phenomena that we have yet to imagine. Beyond telescopes, advancements in computational modeling and artificial intelligence are set to transform how we interpret the data we collect. Simulations of quadruple star systems will become more sophisticated, allowing scientists to predict long-term stability, chaotic interactions, and even the potential for ejected stars or stellar collisions. Machine learning algorithms will sift through vast amounts of observational data, identifying patterns and anomalies that might otherwise go unnoticed. Together, these technologies will act as a bridge between observation and theory, helping us refine our understanding of how these systems form, evolve, and interact over time. And let's not forget the role of gravitational wave astronomy, a field still in its infancy but brimming with potential. While current detectors like LIGO and Virgo focus on binary black holes and neutron stars, future observatories may capture the subtle ripples caused by quadruple systems undergoing dramatic orbital changes. These gravitational waves could provide direct evidence of interactions within these systems, offering insights that light-based observations alone cannot achieve. By combining electromagnetic data with gravitational wave signals, we'll gain a more complete picture of the forces at play in these intricate stellar dances. The implications of these advancements extend far beyond quadruple star systems. As we refine our tools and techniques, we'll also deepen our understanding of the universe as a whole. The discoveries we make about these systems could challenge existing theories of gravity, stellar evolution, and even the conditions necessary for life to arise. For instance, could a planet orbiting within a quadruple system host life despite its chaotic environment? Or might these systems hold clues about the distribution of dark matter? The possibilities are as vast as the cosmos itself. With every new observation, we edge closer to answering these profound questions while opening the door to entirely new mysteries. So, as we look to the future, it's clear that our journey through the cosmos is far from over. The story of quadruple star systems is still being written, and the next chapter promises to be more thrilling than ever. Upcoming telescopes and technologies will not only expand our knowledge, but also inspire a new generation of astronomers to continue exploring the wonders of the universe. Together, we'll keep unraveling the secrets of the stars, one discovery at a time. And now, before we wrap up this cosmic adventure, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update on the mysteries of the universe. Thank you for joining us on this incredible journey. Stay curious, because the best is yet to come. As we draw this cosmic journey to a close, it's hard not to marvel at the sheer complexity and elegance of quadruple star systems. These celestial ballets, with their intricate orbital dances and dynamic interactions, challenge our understanding of the universe while offering a glimpse into the boundless creativity of nature. From the chaotic gravitational tugs of war to the delicate alignments that create breathtaking eclipses, these systems remind us just how much there is to learn about the cosmos. They are living laboratories, testing the limits of our theories and inspiring us to push the boundaries of science. But this isn't the end, it's merely a pause in our exploration. What are your thoughts on these stellar wonders? Share your favorite discovery from today's video in the comments below, and let's keep the conversation going. And remember, the universe is full of mysteries waiting to be uncovered. Stay tuned for more adventures through space and time, because the next revelation could be just around the corner. Thank you for joining us on this incredible journey. Don't forget to like, subscribe, and hit the notification bell so you never miss an update. Until next time, keep looking